You can empty a box. You can take out the dust, pump out the air, strip away moisture, smoke, loose particles, bacteria, atoms. Push matter out of a region of space so completely that, by any ordinary standard, there should be nothing left. And still, physics refuses to call it nothing. That is the first crack. Because nothing sounds simple only at a distance. The moment you try to make it real, not as an idea but as a physical condition, the concept begins to resist you. Empty space turns out to be one of those phrases that feels obvious only until you examine it closely. Then it starts to split open. We live surrounded by things, and that fact has trained our intuition badly. The body trusts surfaces, weight, texture, resistance. The hand closes around matter and comes away convinced that matter is what reality is made of. Even when we look at the night sky and call it empty, what we usually mean is only this: nothing there for us, nothing visible, nothing close, nothing our senses know how to hold. But that is not the same as nothing. Take the most ordinary room. It seems full because it is full of furniture, air, heat, drifting skin cells, light, sound, pressure. Remove the furniture and it still does not feel empty. Remove the air and now the room turns hostile, but not blank. Light still crosses it, radiation still passes through, forces still reach into it, geometry still gives it shape, time still unfolds inside it. Even before physics became mathematically severe, the basic problem was already there. As soon as you try to imagine true absence, the mind keeps leaving something behind. A darkness, a container, a silence, a place. And each of those is already too much. That is why the question is harder than it sounds. Not because it is mystical, but because human intuition is built almost entirely out of experience, inside a world where nothing is never encountered in pure form. We know how to clear a table. We know how to drain a bottle. We know how to step into an empty room. But in every case, the apparent emptiness is still soaked in hidden structure. Air, fields, radiation, motion, law. The closer you look, the less absence you find. And this matters far beyond philosophy, because emptiness is not some rare edge case in nature. It is the dominant condition of the universe. The Earth feels crowded to us because we live crushed against one warm, complicated surface. But that feeling is parochial. Lift away from the ground, and the world thins almost immediately. Higher still, the blue fades to black. The atmosphere that seemed endless from below is revealed for what it is: a fragile film wrapped around rock. Beyond it lies a volume so vast that everything human has ever built, burned, spoken, buried, or dreamed occupies essentially none of it. The universe is not mostly filled. It is mostly separation, mostly intervals, mostly the kind of low-density expanse that tempts language into words like void and nothingness, because ordinary speech has no better handle for scales this indifferent. And yet even that statement conceals another humiliation. The solid world we trust so deeply is itself less solid than it appears. Matter feels compact because the forces inside it are strong, not because it is densely packed in the way common sense imagines. Atoms, the things that make stone feel hard, steel feel rigid, flesh feel substantial, are mostly structured emptiness. Tiny nuclei, diffuse electron distributions, distances and exclusions and rules. The body that feels so continuous is built out of arrangements that would have looked, to an older imagination, disturbingly sparse. So the problem is not only that the universe contains enormous regions we call empty. The problem is that even the things we call full are full in a strange way. Reality is already less substantial than it feels. And that shifts the question. The question is no longer just, what is nothing? The deeper question is, what are we actually removing when we try to make it? What counts as content? What counts as background? At what point does subtraction stop revealing a simpler world and start exposing a deeper one? Imagine the box again, a real box, metal walls, sealed interior. At first it contains ordinary things, air molecules ricocheting invisibly off the sides, traces of vapour, flecks too small to see. Now begin stripping it down. Pump after pump, layer after layer, you lower the pressure. The interior quiets. Fewer collisions, longer intervals between impacts, less of the ordinary bustle of matter. Already, this is a strange act. We are used to creating by adding, building by assembling, filling by supplying. But here the operation is reversed. Knowledge comes through removal. You learn what the world is by taking away what seemed incidental and discovering what refuses to leave. That refusal is the whole story, because every stage of subtraction feels, for a moment, like arrival. Remove the visible particles, surely now it is empty. Remove the gas, surely now it is empty. Remove the contaminants, the residue, the thermal noise. Now, finally, perhaps we are approaching the clean edge of nothing. But each time physics answers with the same cold correction. Not yet. Not yet, because what looked like emptiness was only a coarser form of fullness. Not yet, because the universe is layered. Not yet, because absence, once treated seriously, becomes one of the hardest conditions to define. This is where the subject stops being abstract and starts becoming dangerous to intuition. We do not merely discover that empty space contains more than expected. We discover that our way of dividing the world into something and nothing may have been too crude from the beginning. The distinction feels primitive, human, almost pre-scientific, useful at the scale of cups and rooms and breath, but unreliable once reality is forced into sharper focus. There is a psychological comfort in believing that emptiness is passive, that it is simply what remains when the real contents of the universe are removed. A blank stage, an inert backdrop, a neutral absence against which matter, light, and life perform their brief movements. Physics does not preserve that comfort, because once the vacuum becomes a legitimate object of inquiry, once it is treated not as a poetic idea but as a measurable state, it begins to acquire properties, behaviour, consequence, and from that moment on, the old picture starts to die. Empty space is no longer the opposite of reality. It becomes one of the ways reality hides its deepest structure. That is why this question has survived for so long. It is not a semantic puzzle. It is not a trick of language. It is a wound at the centre of description. The closer we come to the idea of nothing, the more the universe seems to tell us that what we called nothing was only a place where our intuitions stopped working. And long before modern physics made that verdict precise, human beings could already feel the resistance in simpler ways. Try to drink through a straw and block the end. Try to pull space open with your lungs. Try to make a small absence in the middle of an ordinary world. Something pushes back. For centuries, that resistance was interpreted as proof that nature would never permit true emptiness, that the world itself leaned against the creation of a vacuum, that reality, in some deep and stubborn way, preferred being to non-being. It sounds naive now. It wasn't. Because before anyone understood pressure, before air had weight, before the atmosphere became visible as a physical fact rather than an invisible condition, the world genuinely did seem to recoil from emptiness. Tubes collapsed, liquids rose, space refilled itself with almost violent insistence. Again and again, experience seemed to deliver the same verdict. Make a void, and something will rush in to erase it. For most of history, nothing looked less like an absence than a failure. And that is where the descent really begins. Not in the triumph of modern science, but in the older, more intimate confusion. The moment a human being tries to clear a space and discovers that the world does not easily allow it. That resistance made a deep kind of sense. Not because the ancients possessed some hidden truth that modern physics later forgot, but because ordinary experience really does train you to believe that emptiness is unstable. Open a vessel and air floods in. Draw liquid upward and it seems as if the world itself is rushing to prevent a gap. Try to isolate a pocket of absence, and what you encounter is not clean subtraction, but a kind of pressure from all sides. The visible lesson, repeated across daily life, is that voids do not stay voids. They are corrected. From that lived evidence, Aristotle drew one of the most durable conclusions in the history of thought. Nature abhors a vacuum. The line survives now as a slogan, almost ornamental with age, but for him it was not poetry. It was a judgment about how the world behaves. Empty space seemed to create paradoxes wherever you tried to place it. If there were truly nothing somewhere, what would distinguish that nothing from the nothing next to it? How would motion behave in a void? What would stop things from moving infinitely fast through a place offering no resistance at all? Absence was not merely difficult to imagine, it looked physically incoherent, and behind the philosophical problem sat an even simpler, more persuasive one. No one could make a vacuum. That matters. Ideas harden when the world appears to demonstrate them. A doctrine survives for centuries not only because it is elegant, but because reality seems to nod along. Every lungful of breath, every siphon, every rising column of liquid appeared to confirm the same pattern. Space, when emptied, did not remain empty. Something arrived, something pressed, something restored continuity. So the horror of nothingness was never just metaphysical, it was mechanical. Even a straw can show why. Seal one end with your finger, place the other in water and lift. The water comes with it, held in the tube as if gravity has been quietly overruled. Suck the air from a flexible straw and its walls pinch inward. On the surface, these are trivial effects, the kind of household physics so ordinary they barely register, but to a pre-modern eye, they carry a startling message. Where you tried to create absence, the world responded with force. It is easy, with hindsight, to translate that force immediately into pressure difference and move on. But that would miss the psychological reality of the problem. Before pressure had become a quantified, measurable property of matter, these phenomena were eerie. They made the atmosphere act like a hidden hand. Something invisible was clearly doing work. The question was what? And in the absence of a better answer, the old one remained powerful. Maybe emptiness itself is what the world cannot tolerate. There is a severe logic to that belief. The cosmos, as people knew it, was not a sparse abstraction of fields and space-time. It was a packed, inhabited order. Earth below, heavens above, motion with purposes, matter seeking its place. In that picture, a vacuum is not merely an empty region, it is a rupture in the continuity of being, an offence against the grain of the world. That is why the struggle against nothing lasted so long. It was not sustained by ignorance alone. It was sustained by a genuine match between intuition and the scale of phenomena available to human beings. At the scale of breath and vessels and falling water, emptiness really does seem forbidden. The mistake was not stupidity. The mistake was trusting a local truth too far. Because the world of everyday experience is not the world laid bare, it is a filtered world, a world thick with atmosphere, friction, turbulence, thermal motion, hidden forces so constant that they become invisible. We mistake these conditions for reality itself, because they never switch off around us. We are born inside a pressure field and call it normal, born inside a bath of air and forget it is material, born inside one narrow regime of nature and grow arrogant enough to treat that regime as universal. So for centuries, the inability to make nothing was read not as a limitation of tools, but as a law of existence. That reading survived because it did more than explain straws and siphons. It harmonized with the broader human discomfort around absence. Nothingness was always a little obscene. A place without substance, without direction, without the ordinary guarantees of contact and continuity. Better, perhaps, if nature itself refused to permit it. Better if the world had built into it some deep aversion to emptiness. But nature was not objecting to the void. Nature was concealing the atmosphere. That difference changes everything, though it took an extraordinary act of conceptual discipline to see it. To understand why, it helps to linger on how deceptive the air really is. It has almost no visible form. It pours and swirls and compresses without calling attention to itself. It offers resistance only when moving fast enough or when removed. It fills every available space so completely and so habitually that it disappears into the background of thought. Of all the substances that could dominate human life, air is the one most likely to pass for nothing, which means the oldest battle over nothingness was, in a profound sense, a battle with something no one had yet fully learned to treat as something. That is what makes the period so interesting. The world was not wrong about resistance. Resistance was real. Tubes did collapse, liquids did rise, spaces did refill. But the explanation was rotated by 90 degrees. The drama was not that emptiness could not exist. The drama was that the invisible material surrounding us was constantly and quietly enforcing its own presence. We tend to remember the scientific revolution through its grandest images. Planets displaced from the centre, telescopes lifting the lid from the heavens, mathematics replacing inherited authority. But some of the most destabilizing changes came through humbler humiliations, not by looking farther, but by discovering that the familiar world was less transparent than it seemed, that the medium we moved through every second of our lives had weight, that it pushed, that it could hold up columns of liquid, that what looked like a refusal of nothing was in fact the insistence of air. Once that possibility enters the mind, Aristotle's old sentence begins to weaken. Not collapse, not yet, but weaken, because if air is a substance, then many of the phenomena attributed to nature's hatred of emptiness might be reinterpreted without invoking any hatred at all. The world need not be metaphysically hostile to the void. It may simply be physically crowded. The supposed impossibility of vacuum may not be a universal principle. It may be a local consequence of living at the bottom of a dense, gaseous ocean. That thought is already radical, even before it is proved. It replaces an ancient ontological ban with a practical question. Not, can nothing exist, but, can we get rid of what keeps rushing in? And that shift, from philosophy to apparatus, from paradox to experiment, is one of the decisive turns in the story. The void ceases to be merely argued about and becomes something people try to manufacture, to trap, to stabilize, to hold open long enough for nature to answer under controlled conditions. That required a change in temperament as much as method, a willingness to stop asking what the world ought to allow and start building situations in which it must reveal what it actually does. The old claim would no longer be refuted by cleverness alone. It would have to be cornered by matter, by glass, by liquid metal, by weight, by a device simple enough to look almost insulting and strong enough to drag one of philosophy's oldest assumptions into the laboratory. The beauty of what came next is that it did not begin by looking for cosmic mystery. It began with engineers, miners, pumps, practical annoyances. The kind of earthly problems from which revolutionary ideas often emerge when no one is trying to be revolutionary at all. Wells could not raise water beyond a certain height, and the usual explanations had started to fray. Why should suction fail as a fixed limit if nature simply hated empty space without exception? Why would the world tolerate some gaps but not larger ones? Why did the effect seem measurable? The old language was losing its smoothness. Reality was starting to snag on detail, and whenever an old idea starts failing in detail, danger is near, because detail is where inherited pictures begin to bleed. A doctrine can survive broad objections. It can absorb abstractions and reinterpret words, but it struggles when a column of fluid stops at the wrong place, when a phenomenon repeats with numerical stubbornness, when nature ceases to behave like a proverb and starts behaving like an equation. That is exactly the threshold the story was approaching. The world still looked full. The void still looked suspect. Nothing still seemed less like a state of reality than a conceptual wound. But now, for the first time, there were hints that the failure to make empty space might not be final. Only technical. Only conditional. Only a matter of finding the right material, the right geometry, the right way to let the atmosphere reveal itself by pushing against something heavier than water. And once that happened, the old terror of nothing would undergo its first real defeat. Not because humans finally discovered how to make absence pure, but because they learned something more unsettling first. The space around them had never been neutral. It had mass above their heads. It had weight on their bodies. It had been pressing on every attempted emptiness from the beginning. The universe had not been forbidding the vacuum. We had just been trying to create it at the bottom of an ocean we could not see. Once you see the atmosphere as matter, the world changes shape. The familiar stops being familiar. Air is no longer the invisible permission slip for life, no longer the unnoticed background against which real things happen. It becomes a physical substance with pressure, weight, reach, an ocean, not a void. And if that is true, then many of the phenomena that once seemed to reveal nature's aversion to emptiness have to be read in reverse. The world was never recoiling from the vacuum, it was leaning on it. That reversal found its first decisive form in the 17th century, in an experiment so spare it almost feels beneath the scale of the idea it shattered. A glass tube, mercury, a basin, a hand steady enough to turn the apparatus upside down without letting air in. The elegance of the setup matters, because it shows how revolutions often enter the world, not with theatrical complexity, but with a device simple enough to make the old belief suddenly indefensible. Fill a long glass tube completely with mercury, seal the open end, invert it into a dish also containing mercury, then release the seal. If Aristotle had been right in the strongest sense, if the world truly could not permit a void, the mercury should simply have fallen all the way down, the space above it instantly filled by whatever nature required to prevent absence. But that is not what happens. The column drops only part way, then it stops. And above it, something remains. Not trapped air, not hidden vapour in the old sense, not a visible substitute smuggled in to save continuity. Just a region the ancient world would have found deeply offensive. An apparently empty space, suspended there in the tube, held open by the pressure of the atmosphere acting through the mercury below. The force preventing the column from falling is not a hatred of nothingness. It is the weight of the air outside. That is the true violence of the experiment. It does not merely produce a vacuum. It demotes one of humanity's oldest intuitions by revealing that the thing doing the work was beside us all along, unnoticed, because it was everywhere. The man who brought this into focus, Evangelista Torricelli, understood the scale of what had been exposed. His apparatus did more than create an evacuated region. It turned the atmosphere from condition into object. Something you could weigh indirectly, something whose force could be balanced, something that ceased in that moment to behave like absence and started behaving like matter. That is an extraordinary shift. Before this, air was easy to ignore precisely because it never seemed to need explanation. One moved through it, breathed it, watched clouds travel inside it, but did not feel its mass the way one feels stone or water. It lacked the theatricality of ordinary matter. It did not pile up visibly. It did not sit where it was placed. It yielded too easily. It escaped the categories that make substances feel solid to the mind. Mercury changed that, because mercury is heavy enough to force the hidden arithmetic into view. Water could only tell part of the story. Mercury made the pressure of the air measurable in a column short enough to handle, dense enough to balance the enormous sea above us, without pretending suction was some mysterious appetite in nature. The deeper beauty lies in the logic. The apparatus does not banish air from existence, it lets the atmosphere confess itself. The tube becomes a kind of witness stand. The mercury falls, but not all the way, because the world outside the experiment is pressing inward with a force that had been there the entire time. Invisible, constant, forgotten. Torricelli captured that revelation in one of the great compression lines in the history of science. We live at the bottom of an ocean of air. Once heard properly, it is almost impossible to return from, because an ocean is not background. An ocean bears weight. It crushes, supports, circulates, stratifies. It has depth. To say that we live at the bottom of one is to admit that all our everyday experience has been shaped by immersion in a medium we rarely recognize as a medium at all. We do not stand in emptiness punctuated by objects. We live buried under an unseen load. And that means the vacuum, at least in its first modern sense, is not a metaphysical impossibility. It is a local victory against that load. Blaise Pascal understood immediately that this changed more than a single experiment. If the atmosphere truly has weight, then its pressure should weaken with altitude. The higher you climb, the less air remains above you. and if the pressure changes, the mercury column should change with it. That prediction turns the barometer into something even more powerful than a vacuum-making device. It becomes a machine for exposing our place inside the atmosphere. Carry it up a tower or a mountain, and the level falls. Not because the apparatus has changed, but because the ocean around us is thinning. The device becomes a vertical probe through an invisible sea. There is something quietly devastating about that. Every step uphill becomes a subtraction, not of matter from the instrument, but of atmosphere from above the observer. What was once taken as fixed, the pressure of the world, is revealed as contingent, local, layered, variable. The Earth is wrapped, not filled, cocooned, not saturated. And then, beyond that cocoon, the implication widens violently. If the pressure continues to fall as you rise, then eventually the air must end, which means the seeming fullness of earthly life is not the norm of the cosmos. It is a shallow condition, a warm skin clinging to one small world. Above it lies a far more severe reality, a vast expanse where the atmosphere no longer rushes in to erase emptiness, because there is almost nothing there to rush. The vacuum, which once seemed impossible, starts to look like the default. That is one of the great humiliations in the history of thought. Not simply that Aristotle was wrong in detail, but that the world beyond the atmosphere is much closer to emptiness than the human body ever had reason to suspect. The condition we called natural, pressure, air, warmth, dense contact, belongs to a thin margin. Most of reality is not like this. The Earth is the exception. The void is the rule. That sentence lands with more force than it first appears to carry, because it does not merely change our understanding of space, it changes our emotional orientation toward existence. Human life unfolds inside a protected compression. Every breath, every sound, every flame depends on a local abundance that the larger universe does not share. We are not inhabitants of a full cosmos with a few pockets of emptiness. We are creatures of one temporary island, suspended inside an overwhelmingly sparse domain. And yet, even here, at the moment of victory, the story refuses to settle. Because the vacuum Torricelli and Pascal opened was not the final void of modern physics. It was a first wound in the old intuition, not the end of the descent. They had shown that air could be removed, that nature abhors a vacuum was not a fundamental law, that absence, at least of ordinary matter, could be manufactured and stabilized. But that only sharpened the next question. What, exactly, had they made? It is tempting to answer too quickly. An empty space, problem solved. But the history of physics rarely rewards premature closure, and the vacuum is where that mistake becomes especially dangerous. Because as soon as an airless region was created, it began to behave in ways that invited suspicion. Strange ways. Ways that suggested that removing air was not the same thing as reaching true nothingness. A bell placed in such a region could no longer be heard from outside. That made sense. Sound needs a material medium. Without air, its pressure waves have nothing to travel through. Silence, in this case, is evidence of subtraction working exactly as expected. But the bell could still be seen. Light still crossed the evacuated space. That detail seems innocent until you place yourself inside the older logic of waves. By the 17th and 18th centuries, and certainly later, waves were understood through media, sound through air, ripples through water, vibrations through strings. A wave was not a thing floating freely, it was a pattern moving through something. If light behaved like a wave, and mounting evidence suggested that it did, then the vacuum created by Torricelli and Pascal had not settled the matter at all. It had reopened it. Because now the question was more severe than before. Not can empty space exist, but if this space is empty, what is light moving through? That is how one illusion dies, only to give birth to another. The old intuition said vacuum was impossible because the atmosphere would erase it. Torricelli and Pascal broke that intuition, but the moment they did, another need rushed in to fill the gap. Perhaps empty space still contains a subtler substance, invisible and almost impossible to detect, one that carries light the way air carries sound. The vacuum had lost the air. It had not yet lost the medium. And so the region above the mercury column, that first modern pocket of managed emptiness, became something more than a technical triumph. It became a stage on which a new and stranger suspicion appeared. Not that nothingness was forbidden, but that emptiness might be impossible for a deeper reason. That even where matter seemed absent, the universe might still be filled with something more fundamental than matter itself. The first victory over nothing had not delivered pure absence. It had only taught physics how much harder absence would be to prove. The silence was easy to understand. Take a ringing bell, seal it inside an evacuated chamber, and remove the air. Strike the bell again. Its metal still vibrates. The clapper still hits. Motion is still there. But outside the chamber, the sound fades, weakens, disappears. Not because the bell has stopped ringing, but because the medium that carries those pressure waves has been taken away. Sound is not a traveller in its own right. It is a disturbance passed from particle to particle. Remove the particles, and the disturbance has nowhere to go. That part of the vacuum behaved exactly as the new picture said it should. Air was material. Sound depended on it. Empty the chamber, and silence follows. That sight remained. You could still look through the glass and see the bell. This is where the descent tightens, because the vacuum had now become a place where one kind of wave died and another passed freely. That is not a small detail. It is the sort of asymmetry that forces theory to choose what it means by empty. If a chamber without air can block sound but not light, then either light is fundamentally unlike any other wave known to experience, or the chamber is not as empty as it appears. For a long time, the second option seemed far more reasonable. That judgment deserves respect. With hindsight, it is easy to mock the idea that space might be filled with some invisible medium. But once you inhabit the logic available at the time, the conclusion feels almost irresistible. Waves, as far as anyone knew, were motions of something. Water waves moved through water, sound waves moved through air, vibrations moved through strings, wood, metal. A wave without a medium looked less like a scientific insight than a grammatical error. So if light truly was wave-like, as more and more experiments suggested, then the vacuum could not be empty in the absolute sense. There had to be something more refined than air, more pervasive than gas, more elusive than any ordinary substance. Something that filled space even where all visible matter had been removed. Something thin enough to let planets move through it without obvious drag, subtle enough to evade direct detection, yet real enough to support the propagation of light across enormous distances. This hypothetical substance came to be called the luminiferous ether. The name carries an old-world grandeur now, but beneath it was a precise need. Ether was not invented as decorative speculation. It was introduced because physics seemed to require it. Empty space had become conceptually unstable. Light was crossing it too cleanly, too persistently, too universally for the mind to accept that nothing at all lay between source and observer. The vacuum had been cleared of air, but it still looked occupied by necessity. There is a beautiful irony in that. Torricelli and Pascal had broken one ancient ban on nothingness, only for light to reinstall another. The old fear said emptiness could not exist, because ordinary matter would always rush in. The new suspicion said emptiness could not exist, because even when ordinary matter was gone, something more subtle must remain. Physics had emptied the chamber and then, almost immediately, started refurnishing it. And not carelessly. Ether had to be a remarkable substance to do the work demanded of it. It had to permeate all space, including the apparent void between the stars. It had to be transparent because we do not see it. It had to be extraordinarily rigid in one sense, because light moves at an immense speed, and transverse waves usually demand a medium capable of resisting shear. Yet it also had to be ghost-like, because planets sweep through space without the kind of friction one would expect from motion through an ordinary material. The ether had to be everywhere, touch everything, and almost never reveal itself. A less disciplined age might have treated those contradictions as a reason to abandon the idea, but scientific history is rarely so tidy. Often, when a concept begins to strain under impossible requirements, it does not collapse at once. It grows more elaborate, more mathematically refined, more carefully defended. The pressure of evidence and the pressure of expectation begin to interlock. People do not cling to such ideas because they are irrational. They cling because removing them seems to leave a wound in explanation. Ether was that wound dressing. It covered a profound discomfort, the possibility that reality might permit waves without a substance waving. To appreciate how strong that discomfort was, it helps to feel the scale of what ether promised to explain. Light does not merely move through laboratory vacuums. It reaches us from the sun across tens of millions of miles. It arrives from distant stars after crossing expanses so large they dissolve the imagination. Whatever carries light, if anything carries it, must therefore fill not just chambers and tubes, but the entire cosmos. Space itself begins to look less like emptiness than immersion in a medium too subtle for the senses. That thought restored continuity to the universe. It kept the old instinct alive in a more sophisticated form. Empty places were not truly empty after all. The cosmos remained full, perhaps not of air, perhaps not of visible matter, but of an underlying substrate. The vacuum, once again, became a misleading appearance. And with that, the emotional balance of the problem tilted. The vacuum was no longer frightening because it suggested absolute absence. It became fascinating because it seemed to conceal a hidden presence. Not a nothing, but a nearly undetectable something. The conceptual pressure moved from ontology to detection. If ether existed, then the task was no longer to argue about whether nature permitted emptiness. It was to find the medium that had replaced emptiness in the deeper story. The universe had become, in effect, doubly inhabited, first by matter, then by the thing matter sat inside. This is one of the reasons the history matters. It shows how human thought responds when a void opens in explanation. We are often less disturbed by adding an invisible entity than by allowing an intuition to fail completely. Ether preserved the grammar of common sense. It said, yes, reality may be stranger than it looked, but not so strange that waves propagate through sheer nothingness. There is still a hidden flaw beneath appearances. There is still a substance beneath the silence. And for a while, that picture worked well enough to hold the field together. But only well enough, because a concept that explains by being everywhere eventually incurs a debt. If a medium fills all of space, and if the Earth moves through space, then our planet should be moving through that medium. And if we are moving through a medium, then the motion should, in principle, be detectable. The logic is plain enough to feel almost embarrassing in retrospect. Put your hand out of a moving car and you feel the rush of air. Walk through rain and the drops strike differently depending on your direction. Motion through a medium leaves traces. It creates asymmetry, resistance, drift. If ether filled space and the Earth swept through it in its orbit around the Sun, then light itself should betray that motion. Beams travelling with or against the ether wind should not behave exactly like beams travelling across it. That possibility transformed the ether from a useful metaphysical support into an experimental target. And once that happened, the idea entered dangerous territory, because there is a profound difference between a concept that seems necessary in theory and one that can survive precision measurement. In the first stage, imagination does much of the work. In the second, nature begins subtracting freedoms. The medium can no longer be merely subtle. It must be subtle in exactly the right way. It must not just exist, it must answer to apparatus. What makes this moment so tense is that the ether was not yet absurd. It was vulnerable, but not broken. The vacuum still seemed too accommodating to light to be truly empty. The wave picture still seemed too powerful to abandon. The medium still felt like the least violent way to keep explanation intact. But now a line had been crossed. The hidden substance was no longer allowed to remain hidden in principle. It had to submit to a test delicate enough to catch the Earth sliding through it. That is where the story acquires a new texture, not just conceptual, but instrumental. The question becomes whether human beings can build an object fine enough, stable enough, and precise enough to detect a difference so small that most physicists would have considered the attempt nearly impossible. If they succeed, the vacuum will once again be exposed as a disguised fullness. If they fail, something far worse happens, because then the problem is no longer merely that the ether is elusive. The problem is that the vacuum may actually be empty in the classical sense after all. And if that is true, then light is doing something much stranger than anyone wanted to admit. The chamber with the silent bell had quietly opened a trapdoor. The air was gone. The sound was gone. But the light remained, crossing the apparent emptiness with perfect indifference to the old need for a carrier. For decades, ether held that discomfort at bay. It let physics say, the chamber is not truly empty. There is still a medium here, too subtle to feel, but real enough for light. Soon, that reassurance would be placed inside an instrument built to destroy it. And the deepest shock would not be that a hidden substance failed to appear. It would be that empty space seemed able to function without one. The ether was a strangely disciplined fantasy. It was not the kind of idea that grows in the dark corners of science, protected only by vagueness. It emerged from a real demand inside the physics of the 19th century. If light behaved as a wave, then something had to be waving. That premise was so deeply interlocked with every other known wave phenomenon that abandoning it felt less like boldness than sabotage. The ether was what allowed the mathematics of light to advance without detonating the intuitive machinery beneath it. And so, for a time, the vacuum became a different kind of fullness. No longer packed with air or ordinary matter, but saturated by an invisible substrate that no eye could see and no hand could feel. It was supposed to fill the room, the laboratory, the empty chamber, the distance between planets, the gulf between stars. It was everywhere because light was everywhere. A universal medium, finer than gas, more elusive than smoke, woven through all of space so completely that even the void was no void at all. That picture did more than solve a technical problem. It preserved a psychological one. It let the world remain continuous. There is relief in continuity. Relief in being told that beneath the surfaces of experience there is still some hidden thing making the system cohere. Ether offered exactly that comfort. It said that empty space was only an appearance, a limit of the senses, not a genuine absence. Remove air, remove dust, remove matter itself if you like. Still, you have not reached the bottom. There remains a deeper occupancy, a subtle body of the cosmos. The irony is severe. The very success of early vacuum experiments had forced science to admit that air was not nothing. But instead of allowing emptiness to stand on its own, the mind reached for one more layer of substance beneath it. One medium had been removed, another appeared, more abstract and more ambitious, to prevent the conceptual abyss from opening fully. And yet the ether was never allowed to be just anything. The requirements imposed on it became almost cruel. It had to carry light, which meant it had to support wave motion of extraordinary speed. That suggested a degree of stiffness unfamiliar in any ordinary fluid. But it also had to offer essentially no resistance to planets moving through it, which suggested the opposite, an almost perfect lack of drag. It had to be everywhere and nowhere, substantial enough to do indispensable physical work, insubstantial enough to leave the visible mechanics of the heavens undisturbed. It had to be the most mechanically effective substance in nature, and the least mechanically intrusive. You can feel in those demands the strain beginning, not because the concept is instantly absurd, but because reality is starting to ask too much of one hidden entity. Whenever a theory begins to rely on a thing that must possess mutually awkward qualities in order to keep the rest of the structure standing, the danger is no longer philosophical. It becomes experimental. The concept now owes the world a measurable consequence. Ether owed one immediately. If it filled all space, and if the Earth moved through space, then the Earth must move through the ether. That sounds almost childish in its simplicity, but some of the most devastating tests in physics begin exactly there, with a piece of logic so straightforward that the only difficulty lies in measurement. The Earth circles the Sun at enormous speed. If ether is stationary in space while the Earth moves through it, then our planet should be immersed in a constant drift, an ether wind. Light travelling with that wind and against it should not behave in exactly the same way as light travelling across it. A medium, once made universal, can no longer hide from relative motion. This was not a side issue. It was the wound opening at the centre of the ether idea. Because the universe is not static from our point of view. The Earth spins, it orbits, the solar system moves. Any all-pervading substrate should eventually betray itself by allowing motion through it to be detected. One direction should become privileged, One beam of light should be ever so slightly delayed or advanced compared with another. The vacuum, if filled with ether, should become anisotropic under measurement. Not visibly, not dramatically, but enough. Enough is where the challenge became savage. The difference expected from the Earth's motion through the ether was tiny, staggeringly tiny relative to the enormous speed of light. Not the sort of discrepancy one could expose with rough instruments or broad observational habits. To test the idea, physicists would need a new kind of precision, a way of splitting light, sending it down different paths, recombining it, and watching for minute shifts in the resulting interference pattern. The effect, if it existed, would be less like a gust of wind and more like the faintest tremor in symmetry. This is where the story stops being about conceptual plausibility and becomes a matter of craftsmanship. The ether was not going to be overthrown by rhetoric. It would be cornered, if at all, by apparatus. Mirrors aligned with near maniacal care, optical paths balanced to absurd delicacy, vibrations suppressed, noise minimized, the whole world made still enough that an invisible drift through space might disclose itself in the behavior of light. There is something beautiful about that transition. The vacuum ceases to be a place where people project their metaphysics and becomes a place where they place demands on reality itself. No more appeals to what waves ought to need. No more confidence that continuity must be preserved somewhere beneath appearances. Build the instrument. Rotate it. Let the light answer. Before that answer came, though, it is worth pausing on how much was at stake. If the ether were detected, then the vacuum would remain, in one important sense, classically respectable. Empty of ordinary matter, perhaps, but not a true absence. Space would still possess a hidden occupant, a substrate granting light its means of propagation. The old instinct would survive in upgraded form. Emptiness, once again, would turn out not to be empty. But if the ether failed to appear, then the problem would become much more severe than a single discarded medium, because then physics would be forced into a position it had resisted for generations, accepting that light might not need a carrier in the familiar mechanical sense at all. Accepting that empty space could transmit something fundamental without itself being filled by a substance. Accepting, in other words, that the grammar of common sense waves had reached its limit. That is why the ether matters, even though it was wrong. A false idea can still be structurally noble. It can reveal what a scientific culture is prepared to sacrifice last. In this case, what physics was prepared to sacrifice last was the conviction that process must always belong to a medium. Ether was the final defense of that conviction, the final attempt to save continuity, to save the intuition that every propagation needs a bearer, every motion a thing moved, every wave a body to undulate through. When people later speak as if modern physics abruptly became weird, they often skip this stage. But the weirdness did not arrive all at once. It had to be earned by exhausting the alternatives that would have made reality feel less alien. Ether was one of those alternatives, an elegant, necessary-seeming compromise between observation and instinct, a way to keep the void from becoming too void-like. And because it was so necessary-seeming, its destruction would matter far beyond optics. It would mean that the vacuum, stripped now not just of air but of any classical supporting substance, could no longer be thought of as a disguised material plenum. Space itself would become more austere, less intuitive, harder to domesticate. The absence inside the evacuated chamber would lose its last obvious occupant, and that would force physics to confront a stranger possibility. Perhaps the emptiness between things is not a hidden kind of matter at all. Perhaps it is something more abstract, more severe, more structurally fundamental. But the ether did not die because someone mocked it. It died because a particular kind of mind was willing to chase absurd precision. Albert Michelson belonged to that breed. He was not content to repeat the general truth that light moves quickly. He wanted to know how quickly, exactly, and whether differences too small for ordinary perception might still be made visible through interference. He was drawn to the kind of problem most people sensibly avoid, problems where the expected signal is so faint that the entire experiment seems to balance on the edge of futility. That temperament matters because reality often yields its harshest answers only to those patient enough to build a question delicate enough to deserve one. The instrument Michelson would eventually help create was, in spirit, a trap for asymmetry. If Earth was drifting through ether, the motion should leak into the light. One path should take slightly longer than another. Rotate the apparatus and the relationship should change. The pattern should slide. Not by much, but enough to expose the universal medium that had been drafted to fill the vacuum. This is the moment where the old picture stands at its most vulnerable and its most dignified. Ether is no longer mere comfort. It is a hypothesis walking toward judgment. And whatever the outcome, the vacuum is about to change character again. If the pattern shifts, then empty space is still secretly inhabited. If it does not, then the chamber with the silent bell has been telling the truth more ruthlessly than anyone was ready to hear. Because then the air would be gone, the medium would be gone, and light would still cross the darkness. And so the question narrowed to almost nothing. Not to the grand emptiness between galaxies, not to the philosophy of non-being, but to a tiny difference in the travel time of two beams of light. That is often how reality protects itself. The largest revisions do not announce themselves at their true scale. They arrive disguised as measurement problems, a fringe shift, a delayed signal, a discrepancy so small it seems unworthy of the metaphysical weight it is carrying. But if the ether existed, then this was enough. The Earth's motion through it should leave a trace in light itself. Not because the cosmos wished to reveal its hidden medium, but because motion through any medium creates asymmetry. It privileges one direction over another. Albert Michelson understood that if the effect was real, it would be ferociously subtle. The speed of light is so immense, and the Earth's orbital motion so comparatively slight, that the expected difference was buried inside a ratio almost insulting in its smallness. You were not looking for a great tearing wind through space. You were looking for a faint imbalance riding inside one of the most stable quantities in physics. That demanded an instrument of unusual seriousness. The apparatus Michelson eventually built with Edward Morley was not complicated in the way a machine can be complicated by sheer size or moving parts. Its power came from refinement. A beam of light is split in two. The two beams travel along perpendicular paths, bounce from mirrors, and return to recombine. When they overlap, their wave nature produces an interference pattern, bright where the peaks reinforce each other, dim where they cancel. If one beam takes even slightly longer than the other, the pattern shifts. That shift was the entire wager. Build the instrument, rotate it, let one arm point into the supposed ether wind, then across it, then away from it. If the Earth is moving through a stationary medium, the travel times should change with orientation. The interference fringes should slide across the detector. The vacuum would reveal itself not as emptiness, but as immersion. There is something almost ceremonial about the design. It does not demand that the universe explain itself in words. It sets a trap for preference. If space contains a medium, one direction must matter more than another. The instrument asks only for that inequality. Everything else was precision, mirrors, stability, isolation from vibration, patience. The original apparatus rested on a heavy stone slab floating in mercury, an effort to let it turn smoothly while protecting it from tiny disturbances that could swamp the very effect being sought. It was, for its era, a machine built at the edge of what experimental finesse could manage. Not because the question was flamboyant, but because it was mercilessly exact. And almost everyone expected it to work. That matters. The Michelson-Morley experiment is often remembered through the drama of its null result, as if the ether was already a suspect concept lumbering toward deserved collapse. It was not like that. The ether was a serious, almost unavoidable component of the best available picture. Michelson and Morley were not iconoclasts setting out to detonate orthodoxy for sport. They were trying to detect what the structure of 19th century physics had given them every reason to believe was there, which is part of what made the answer so unnerving. They looked. They rotated the apparatus. They watched the pattern. And the expected shift did not arrive. No ether wind announced itself. No preferred direction emerged. No matter how the instrument was turned, the speed of light appeared stubbornly unchanged. The difference that should have betrayed Earth's motion through the medium failed to show itself. Not once in some conveniently dismissible way, but persistently, carefully, with enough stubbornness to begin corroding the idea the experiment had been built to confirm. That is the true violence of the result. Not that it produced a dramatic contradiction, but that it produced almost nothing at all. A null result, when it lands on the right target, can be more devastating than a positive signal. It removes excuses. It hollows out a concept from within. The instrument had not malfunctioned in the ordinary sense. It had performed its task with exquisite sensitivity, and what it kept returning was the same austere answer. The asymmetry expected from motion through the ether was missing. The universe had refused to privilege a direction. At first, that did not immediately kill the ether. Physics is rarely so quick to surrender something that deeply woven into its explanatory fabric. Alternative fixes were proposed. Perhaps matter itself changed shape as it moved through the ether. Perhaps the instrument contracted along the direction of motion just enough to hide the effect. Perhaps the medium behaved in ways more cunning than the original picture allowed. These were not irrational evasions. They were the last technical maneuvers of a worldview trying to preserve continuity under experimental assault. But a line had been crossed. The ether was no longer the calm background assumption it had once been. It had become a burden. Every failed detection, every rescue attempt, every additional adjustment made the concept more strained, more conditional, less like a necessary foundation and more like a story being kept alive by compensations. And this is where the vacuum changes character in the deepest classical sense. Because until now, every revision had still tried to preserve some kind of hidden occupancy. The air was there. Then the ether was there. Remove one layer of obvious substance, and another, more subtle layer took its place. Reality kept refusing to yield an actual emptiness. The void, whenever approached, seemed to acquire a new tenant. Michelson and Morley stripped away the last respectable tenant of that kind. Not all at once, not with a single theatrical pronouncement, but with an experiment so clean in logic and so unsettling in outcome that physics could no longer assume a material support for light without paying an ever-growing price. The vacuum, at least as classical intuition had imagined it, had lost its final substance. That left a harsher question exposed. If light needs no medium, what exactly is moving? The old answer had been mechanical. A wave is a state of some material thing. Water rises and falls. Air compresses and rarefies. A string bends and relaxes. But now light remained perfectly real, while the thing it was supposed to be waving in had vanished under scrutiny. That was not merely an optical inconvenience. It was a wound in the common-sense architecture of physics. The resolution would come from a different line of thought already gathering force. James Clerk Maxwell's equations had unified electricity and magnetism into a single structure, and in doing so, revealed light as an electromagnetic wave. That was already a profound shift. Light was not a ripple in matter after all, but an oscillation in electric and magnetic fields. The mathematics itself implied a propagation speed, the very speed of light, as if nature had quietly embedded optics inside electromagnetism all along. But Maxwell's theory, magnificent as it was, still lived in uneasy coexistence with the ether picture for many physicists. The fields themselves were often imagined as states of the ether, rather than replacements for it. Michelson and Morley made that compromise increasingly unstable. If the medium could not be found, perhaps the fields did not require one in the old mechanical sense. That possibility ripened into one of the great acts of intellectual severity in modern science. In 1905, Einstein took the constancy of the speed of light seriously enough to let it break the framework around it. He did not save the ether by making the result more complicated. He accepted the result and allowed space and time themselves to become the things that had to change. Simultaneity lost its universality. Length and duration became dependent on motion. The laws of physics, including the speed of light in vacuum, were required to take the same form for all inertial observers. This was not a decorative revision. It was the price of a new honesty. Instead of insisting that light behave like an ordinary wave in an ordinary medium, relativity accepted that empty space could host electromagnetic propagation without being filled by a classical substance. The vacuum was no longer a disguised material plenum, it became something more austere. Not nothing in the careless everyday sense, but not a hidden fluid either. A domain in which fields could exist and light could travel without the old mechanical carrier intuition surviving intact. The chamber with the silent bell had been telling the truth, only not the whole truth. Air was gone, and sound with it. The medium was gone too, and light still crossed the darkness. That is one of the great moments in the history of emptiness, because it feels, for an instant, like a rival. The atmosphere has been exposed, the ether has been removed, the vacuum has been cleared of every obvious occupant. Space, at last, seems to stand empty in the classical sense. A kind of pristine stage on which matter and radiation merely appear and vanish, leaving the background itself clean. For a moment, physics could almost believe that. For a moment, the void looked simple, and that moment did not last. Because just as the classical vacuum was finally being stripped to its barest form, industry learned how to manufacture it at scale. Bulbs, valves, tubes, chambers, devices that depended on controlled emptiness began to spread through the modern world. And the better we became at making vacuums, the more ruthlessly the small-scale structure of nature began to answer back. The old medium was gone, but the emptiness left behind was about to become far stranger than any medium ever was. That was the second humiliation. The first had been learning that air was not nothing. The second was learning that once the vacuum finally looked clean, useful, and conceptually tamed, it became a tool. And tools have a way of forcing theory past the point where theory feels comfortable. By the late 19th century, empty space was no longer only a philosophical scandal or a laboratory curiosity. It had become something engineers could manufacture, improve, standardize, sell. What had once seemed like a wound in the texture of nature was turning into infrastructure. There is a strange elegance in that reversal. Human beings did not first understand the vacuum completely and then put it to work. They learned to exploit it while still misunderstanding it. They learned how to seal off regions of space, pump them down, preserve them inside glass, and build devices whose operation depended on the absence of ordinary matter, long before the deeper character of that absence had settled. That is often how science actually advances, not by waiting for perfect ontology, but by building machines that function well enough to expose the inadequacy of the concepts surrounding them. A light bulb is one of the simplest examples and one of the most revealing. Heat a filament until it glows white hot, and in open air it burns away almost immediately. Oxygen attacks it. The brilliance is brief. But evacuate the bulb, remove most of the reactive gas around the filament, and the same wire can burn with controlled intensity for far longer. Darkness retreats from streets and rooms because someone learned how to bottle a small region of managed emptiness. That detail is easy to trivialize now, because the modern world is saturated with technologies whose conditions of possibility have become invisible. The bulb glows, and we no longer feel the vacuum inside it as part of the event. But it is. The light comes not just from the filament, but from the engineered absence surrounding it. The device works because matter has been partially denied the chance to interfere. That pattern repeated everywhere. Vacuum tubes made early electronics possible. Radios, amplifiers, oscilloscopes, televisions, switches, the first generations of electronic computation, all depended, in one form or another, on particles moving through evacuated regions more freely than they could have through ordinary air. Engineers were discovering that emptiness could be operational, that removing the clutter of matter was not merely subtractive, it could create new regimes of behavior. This is the point where the vacuum stops being a backdrop and starts becoming a condition you can tune. Pressure down. Contaminants out. Mean free path longer. Collisions fewer. Control improved. The interior of the device begins to feel less like a passive hollow, and more like an environment with its own engineered character. Not full, exactly, not alive in the modern quantum sense yet, but already not blank, already not just nothing there. It is a crafted state in which nature behaves differently because ordinary interference has been reduced, and that difference mattered far beyond technology. As vacuums became easier to produce, cleaner to maintain, and more stable to work with, physics acquired something more precious than a useful industrial trick. It acquired a new experimental territory. If air was constantly colliding with everything, obscuring delicate effects, then a vacuum became a way of quieting the world enough to let smaller truths emerge. It was not only that devices needed emptiness, discovery needed it. Better vacuums meant cleaner beams, more controlled discharges, more reliable interactions between matter and radiation. The small-scale world, which had always been there, began to answer with new sharpness once the noisy burden of the atmosphere was partly removed. That is why the history of vacuum technology and the history of modern physics are so deeply entangled. By learning how to empty space more effectively, we unintentionally built a clearer doorway into the microscopic structure of reality. And the microscopic structure was waiting with bad news for common sense. Inside evacuated tubes, strange glows appeared. Cathode rays, X-rays, electrons. Phenomena that did not fit comfortably inside the older picture of matter as continuous, solid, and intuitively substantial. The atom, which had long functioned as a philosophical endpoint, the smallest indivisible unit, began to reveal internal structure. Charge could be separated. Radiation could penetrate. Scattering experiments started to imply that what looked solid was mostly arrangement, mostly distance, mostly force. There is a kind of narrative cruelty in that progression. The vacuum had already wounded the idea that emptiness was impossible. Now it was helping wound the idea that fullness was simple. The same technological power that let humans clear out regions of space was also exposing how little of ordinary matter was matter in the dense, bodily sense the mind instinctively prefers. The atom did not turn out to be a miniature pebble. It turned out to be an architecture, a nucleus astonishingly small relative to the volume it governs. Electrons described not as tidy orbiting marbles in the crude picture, and later something stranger still, distances dominating occupancy, rules dominating contact, matter becoming less like packed substance and more like organized possibility. Which means the vacuum was attacking intuition from both sides at once. First, the supposedly empty was not simply empty. Then, the supposedly solid was not simply solid. There is no stable refuge for common sense in that pincer movement. If emptiness is more structured than it looks, and matter more sparse than it feels, then the ancient contrast between something and nothing begins to lose its clean edge. The world no longer divides into substantial objects set against a neutral absence. Both terms become suspect. Both require rebuilding. This is why the industrial phase of the vacuum matters so much to the deeper story. It is not a detour through gadgets. It is the stage where emptiness becomes repeatable, controllable, and therefore fertile. The vacuum is no longer a one-off philosophical embarrassment staged by mercury and glass. It becomes a routine condition in laboratories and devices, and under that condition, nature starts disclosing layers of itself that would otherwise remain washed out by ordinary air. The more quietly we could make space, the louder the microscopic world became. That is a line worth taking seriously, because what came next was not merely another collection of discoveries, it was a breakdown in the classical idea of what a description of nature ought to be. The old world, the world of billiard ball causes, definite positions, continuous trajectories, measurable properties possessed at all times whether or not anyone looks, had survived the death of the ether. It had been shaken, but not ruined. One could still imagine a clean vacuum as a passive stage, and matter as the active cast. The quantum world ended that comfort, and the entrance point was subtle, not a great explosion of absurdity, but a growing set of precise failures in the classical account. Blackbody radiation, the photoelectric effect, atomic spectra, stable atoms that classical electrodynamics struggled to explain. Each problem might have looked local at first, a technical mismatch, an irritation in the equations, but together they formed a pattern. The small-scale world was not obeying the grammar of certainty in the way 19th century physics expected. This matters for the vacuum, because once you move into the quantum regime, emptiness is no longer judged merely by whether ordinary matter has been removed. It becomes entangled with a harder question. What does it even mean for a system to have nothing happening at the smallest scales? What does stillness mean when the very notion of definite state begins to loosen? What does zero mean when the world refuses the kind of exactness classical intuition demands. That is where the vacuum becomes dangerous again. For a little while after Michelson and Morley, it had seemed that the void might finally be classically austere. No air, no ether, just empty space hosting fields and light. Strange, yes, but conceptually clean. The industrial era sharpened that picture by making vacuums more real and more useful. But the very success of those manufactured emptinesses created the conditions for a more devastating discovery. At sufficiently small scales, certainty itself starts to fail. Not because the instruments are clumsy, not because the experimenters are ignorant, because reality, in that regime, is not built to give simultaneously exact answers to the kinds of questions common sense wants to ask. This is the threshold where the story takes on a new kind of tension. Up to now, the vacuum has mainly been a problem of hidden occupancy. Is there air? Is there ether? Is there some medium left behind when visible matter is removed? But quantum theory begins shifting the tension away from contents and toward the structure of physical description itself. The instability is no longer just in the vacuum, it is in the terms by which we try to define what the vacuum would be. That shift is easy to underestimate because the phrase uncertainty principle has been dulled by overuse. It sounds almost familiar now, a slogan from modern science softened by repetition. In truth, it marks one of the hardest blows ever dealt to naive realism at small scales. It says, in effect, that the world is not merely difficult to measure completely, it is not completely there in the way classical habits of thought assume. And once that enters physics, a vacuum can no longer be understood simply as a region in which all contents have been removed. Because if nature itself does not grant exact stillness and exact content in the old way, then nothing is going to become much harder to define than even the death of the ether had prepared us for. The old emptiness had been stripped of air, then stripped of medium. Now it was approaching a scale where even the idea of perfect quiet would begin to fracture. That fracture begins with a limit on what the world will let you know at once. Not as a matter of clumsy instruments, not as a confession of human weakness, as a structural feature of nature itself. This is the point where classical intuition starts to fail in a more intimate way than before. The earlier humiliations were about what filled space. Air had been there when we mistook it for nothing. Ether had not been there when we insisted it must be. Those were severe corrections, but they still left intact a deep assumption about reality, that things possess exact properties in exact ways, and that if we are clever enough, patient enough, delicate enough, we can, in principle, uncover them all together. Quantum mechanics does not preserve that assumption. At the scales where electrons, atoms, and radiation begin to dominate the story, the problem is no longer simply that reality is hidden. The problem is that reality is not organized according to the clean, simultaneous exactness that common sense expects. Position and motion do not settle into precise values together just because we demand they should. The world withholds that kind of completeness. Heisenberg gave that withholding its sharpest form. The uncertainty principle is often introduced as if it were a sort of modern parable about measurement disturbing what it observes. That is not entirely wrong at a crude pedagogical level, but it misses the severity of the point. The deeper issue is not merely that we interfere with microscopic systems when we probe them. The deeper issue is that the mathematical structure of quantum theory does not allow certain pairs of physical quantities to be jointly sharp in the classical way. The indeterminacy is not just in our tools, it is in the regime itself. That is why the principle matters so much to the vacuum, because emptiness, up to this point, still carried a classical dream inside it. Remove the contents, and what remains will be perfectly still, perfectly defined, perfectly quiet. A true zero, a clean baseline. Quantum mechanics begins dismantling that dream from the ground up. It helps to approach the problem through a contrast the body can almost feel. Imagine a still photograph taken at extremely high resolution. Freeze a moving object, a ball crossing a table, a drop of rain, a bird in flight, and if the exposure is short enough, the image can pin its position with great clarity. The edge is crisp. The location is exact or close enough for every ordinary purpose. But the image does not really tell you motion. It hints at it, perhaps, but only weakly. It captures where, not how. Now imagine a video of the same event, recorded over time. Suddenly you gain motion, direction, speed, sequence. The object is no longer nailed to a single place. It is distributed across moments. And if you zoom too closely into a single frame from a compressed, time-rich recording, the spatial precision often degrades. You bought dynamical information by spreading certainty across time. The analogy is imperfect, but it gestures at the trade built into the quantum world. The more sharply one kind of description is enforced, the less sharply another can coexist with it. Position and momentum are not jointly available in unlimited clarity. The microscopic world does not present itself as a catalogue of exact hidden values, waiting politely to be read off all at once. This is not mysticism. It is disciplined cruelty, because it means that the classical picture of a particle as a tiny object with a perfectly definite location and a perfectly definite motion at every instant is not merely hard to access. It is not the form in which quantum theory delivers reality. The old image begins to crack. What remains is not chaos, but a deeper order whose logic is statistical, wave-like, amplitude-based, and far less hospitable to intuition. At first, this may seem remote from the vacuum. It sounds like a problem about electrons or atoms, not about empty space. But the connection is direct and lethal to the old idea of nothing. Because once uncertainty enters physics at the foundational level, you can no longer imagine an empty region of space as possessing exactly zero of everything in the simple classical sense. The notion of a perfectly silent baseline becomes unstable. To understand why, it helps to avoid one common mistake. Quantum uncertainty does not mean anything can happen in some lazy slogan-like sense. It means specific quantities are linked by precise limits. There is rigor in the indeterminacy. The theory does not dissolve the world into vagueness. It replaces one form of exactness with another, one less intuitive, but far more faithful to experiment. An experiment is what forced this worldview into existence. Atomic spectra did not emerge as blurred accidents. They came in discrete lines. Electrons did not radiate energy in the continuous classical way expected of orbiting charges. Blackbody radiation resisted every conventional treatment until quantization entered. The photoelectric effect implied that light itself arrived in packets under the right conditions. Everywhere physicists looked at the microscopic world with sufficient care, the classical language of continuity and certainty began to snag. Reality was still lawful, but the laws were no longer psychologically comforting. This is what makes the transition so important for the story of emptiness. The vacuum had seemed, for one brief classical interval, like a clean stage stripped of hidden material substance. But quantum theory now raises a more dangerous question. Even if the stage contains no particles in the obvious sense, what entitles us to think the stage itself can ever be perfectly still? Perfect stillness, after all, is just another way of demanding simultaneous certainty, exact values, exact quiet, exact baseline. The quantum world does not hand out exact baselines for free. If you confine something tightly in space, you force uncertainty into its momentum. If you demand sharply defined conditions in one respect, fluctuation appears in another. The deeper lesson is not that the world is noisy in a sloppy sense. It is that quietness has structure. The lowest energy state of a system is not automatically the classical image of dead stillness. Even the ground floor may retain motion, spread, indeterminacy. Once you really feel that, the vacuum starts becoming dangerous again. Because what is an empty box in physical terms? It is not merely a shape from which matter has been removed. It is a region to which one is implicitly assigning properties. No particles here, no activity here, no energy here, no change here. But quantum theory has begun warning us that such assignments may be too blunt, too classical, too innocent. The box is not just a container. It is a demand placed on nature. We say, here, inside these walls, let there be nothing. Let there be no ordinary stuff, no obvious motion, no detectable content. And quantum mechanics replies, you may reduce the contents, but do not mistake reduction for absolute zero. Do not confuse your subtraction with the universe's own accounting. This is where the emotional temperature of the story changes. Earlier, the vacuum was destabilizing because it threatened to contain hidden substances. Now it becomes destabilizing because, even after those substances are removed, the regime itself may resist perfect quiescence. The problem is no longer simply occupancy, it is whether absence can ever be exact. There is a severe beauty in that shift. Science often proceeds by purifying a concept, cutting away confusion, hidden assumptions, inherited metaphors, until the thing stands bare. But with the vacuum, purification keeps revealing deeper contamination. Not contamination by dirt or gas or invisible fluid, but by the structure of law itself. The concept does not become cleaner as we refine it, it becomes harder to finish. And the route into that next layer runs through a different expression of uncertainty, one even more dangerous than the familiar trade between position and motion, because uncertainty can also be written in terms of energy and time. That matters in an almost unforgiving way. Classical emptiness imagines a region of space with exactly no energy content beyond the trivial baseline, a calm zero, a floor with nothing happening. But if the more briefly you examine a system, the less sharply energy can be pinned down, then over sufficiently tiny intervals, the vacuum may not be allowed to sit at a perfectly exact zero in the classical sense. The shorter the timescale, the less rigid the bookkeeping becomes. This is the edge, where emptiness stops being a static concept and starts becoming a dynamic one. Not because particles are visibly flashing into and out of existence all around us in the coarse world of daily perception. They are not, at least not in any naive cinematic sense. But because the mathematical structure of quantum theory begins to deny that the lowest activity state is equivalent to literal nothing happening. The vacuum starts to look less like a blank and more like a minimum, the quietest state allowed perhaps, but not the classical void of absolute nullity. That distinction is everything. A blank is simple. A minimum is lawful. A blank is what intuition wants. A minimum is what physics is willing to give. And that means the ancient hope of reaching true nothing by successive subtraction is about to suffer its deepest defeat so far. Not because we failed to remove enough matter, not because a hidden ether slipped back in, but because the world, at its smallest scales, does not seem built to let exact emptiness sit there in perfect classical silence. The vacuum had already survived the removal of air. It had survived the death of the medium. Now it was about to survive the demand for absolute stillness. Now the idea becomes dangerous enough to misunderstand. Because the moment energy and time enter the story, popular language tends to rush in and flatten everything into a slogan. Particles borrow energy from nothing, briefly appear, then pay it back. It is a memorable image. It points in roughly the right direction. But taken too literally, it turns the vacuum into a kind of cosmic accounting scam, as if nature occasionally relaxes its laws for dramatic effect. That is not what is happening. The laws are not being suspended. They are being obeyed in a regime that does not resemble classical stillness. What quantum theory tells us is subtler and more severe. If a system is examined over an extremely short interval, the notion of its energy being pinned to one perfectly exact value becomes less rigid. The shorter the temporal scale associated with the description, the looser the classical image of exact energy bookkeeping becomes. This is not a license for chaos. It is a statement about the structure of quantum states, the limits of simultaneously sharp descriptions, and the fact that the vacuum in quantum theory is not defined as nothing whatsoever, but as the lowest energy state of the fields involved. That phrase matters, the lowest energy state, not the absence of reality, not the absence of law, not a blank page underneath existence, a physical state. Already that is a profound reclassification. The vacuum is no longer being approached as a hole cut into the world. It is becoming a particular condition the world can be in, a condition with rules, with measurable consequences, with a structure that only begins to show itself when classical expectations are pushed past their range of validity. To feel the force of that, imagine returning to the box, but now with a more disciplined eye. You do not ask, have I removed everything? Because physics has already warned you that everything is too crude a category. You ask a harder question. What is the quietest state that space itself can physically occupy? That is an entirely different question. It shifts the problem from subtraction to ontology. Not what remains after we scrape the interior clean, but what reality itself permits as a baseline. And quantum theory gives an answer that is both more precise and less comforting than intuition would like. The vacuum is quiet, yes. Quieter than states containing actual particles that can be detected as matter or radiation in the usual way. But it is not classically dead. It is not an inert emptiness that simply waits around for real things to happen inside it. It is the ground state of an active framework. This is where the conceptual temperature rises sharply, because once emptiness is redefined as a physical ground state rather than literal non-being, the old opposition between nothing and something starts to degrade almost beyond recognition. The vacuum is not nothing in the philosophical sense, but neither is it something in the ordinary sense of a substance sitting there like dust or gas or fluid. It occupies a harder category: structured absence, lawful baseline, minimum energy configuration, a regime whose very quietness turns out to have content. That content does not mean that particles are just constantly popping around in the coarse, visual way people often imagine. Quantum field theory is stricter than that language suggests. Much of what later gets described with phrases like virtual particles is best understood as a calculational and conceptual way of describing interactions and fluctuations within the fields, not as tiny billiard ball objects literally appearing in the same way ordinary particles do. The vacuum is restless, but not cartoonishly so. Still, restless is the right direction, because once fields become the fundamental language, emptiness inherits their existence. This is the decisive move. In the older classical view, one could imagine space as a container and matter as what occupied it. Then, perhaps, light and electromagnetism complicated the picture. But in quantum field theory, the world is not fundamentally built out of little objects placed into an otherwise neutral emptiness. It is built out of fields, and what we call particles are excitations of those fields. The vacuum is what remains when those fields are in their lowest accessible state, not absent, but unexcited in the ordinary particle sense. So even at its most stripped down, the universe is not gone. Its framework remains. Its possibilities remain. Its lawful susceptibility to excitation remains. And that means the vacuum can no longer be imagined as a place where nothing whatsoever is present. The fields are there. Their ground state behavior is there. Their fluctuations, encoded in the formalism and in measurable consequences, are there. The empty box is now embedded in a reality that cannot be reduced to a literal blank. This is the midpoint where the story truly changes shape. Up to now, each stage of the descent has mostly removed an illusion. Air was not nothing. Ether was not real. Classical emptiness was not the final answer. But here the script has to do something more than dismantle. It has to replace. And the replacement is this. The vacuum is not the subtraction of the world. It is one of the world's states. A state so quiet that common sense mistakes it for absence. A state so fundamental that later physics will start building entire explanations on top of it. That shift has consequences immediately. If the vacuum is a state of fields rather than a blank stage, then the possibility opens for temporary, local structure to be associated with it in ways that classical emptiness would forbid. Not arbitrary structure, not unconstrained magic, but lawful fluctuations encoded in the formalism capable under the right circumstances of affecting measurable systems. This is why energy and time uncertainty matters so much in the narrative spine. It is the place where zero loses its innocence. Classically, zero is a dead floor. No motion, no process, no residue. Quantum mechanically, the floor can still have texture. And once the floor has texture, all sorts of old assumptions begin to fail. The vacuum can influence atomic behavior. It can contribute to measurable shifts. It can enter cosmology. It can become entangled with the origin story of large-scale structure. It can even, in one of the deepest unresolved problems in theoretical physics, confront us with the catastrophic mismatch between vacuum energy estimates from quantum field theory and the observed smallness of the cosmological constant. That last issue will matter later. For now, it is enough to understand the logic of the turn. We are no longer chasing hidden occupants of space. We are confronting the fact that the ground state of a quantum world is itself not trivial. That is a harder truth than any ether. An ether still preserves the old comforts that emptiness is secretly full of some medium, some thing. But a quantum vacuum is more unsettling, because it is not just another substance placed inside space. It is what empty means once the world is described in terms of fields and their lowest energy behavior. The disturbance is no longer imported from outside. It is built into the baseline. This is why the vacuum becomes one of the great pressure points between intuition and physics. Human thought wants reality to bottom out in stillness. We want the last layer, the stripped core, the final remainder after all subtraction, to be simple, silent, frozen. The quantum world refuses that wish with almost impersonal elegance. The quietest state is not nothing, it is a minimum. And a minimum can still fluctuate. From here, the next step becomes unavoidable. If the vacuum is the lowest energy state of the fields, and if the formalism permits fluctuation-like effects around that baseline, then what sort of structure can briefly manifest there? What kinds of pairs, processes, and measurable consequences emerge when relativistic quantum theory is allowed to describe the world honestly enough? This is where a new mind has to enter the story, not just because history demands a name, but because the conceptual machinery is about to become too strong to move without one. Quantum mechanics has already destabilized classical stillness. Relativity has already severed light from any mechanical medium, but the full violence of the vacuum will not appear until those two great frameworks are brought together, and when they are, the result will not simply refine the picture of empty space, it will double it. Because Paul Dirac's equations will force physics to confront a mirror architecture inside matter itself, one in which emptiness is no longer merely restless, but capable of pairing the world with its opposite. The old void had already refused to stay blank. Soon it will refuse to stay single because relativity and quantum theory, left apart, could no longer be trusted. That was the crisis waiting beneath all the other crises. By the late 1920s, physics possessed two frameworks of astonishing power, and they did not sit comfortably together. Quantum mechanics governed the microscopic world with brutal success. Einstein's special relativity governed high speeds with equal authority. But the universe is not polite enough to keep those regimes separate. Electrons inside atoms are small enough to be quantum objects, and energetic enough that relativity cannot be ignored completely. The world was asking for a description that honoured both truths at once. Without that union, the picture remained broken. The need was not cosmetic. It was not a matter of mathematical tidiness. If the foundational theories of the small and the fast could not be made to coexist, then one or both would eventually have to yield. Nature does not owe us consistency in our equations, but if our best descriptions fracture precisely where reality demands overlap, then the fracture is ours, not hers. This is where Paul Dirac enters the descent, and he matters not simply because he was brilliant, but because his kind of brilliance was unusually suited to the task. Some physicists think by verbal pressure, by conceptual argument, by restless physical intuition expressed in language. Dirac seemed to think with a colder instrument. He pursued elegance not as ornament, but as a diagnostic. For him, mathematical beauty was not decoration draped over truth. It was often the sign that one had found a structure deep enough to deserve belief. That can sound mystical if stated badly. In Dirac's hands, it was not. It was severe. He wanted equations that did not merely work, but compressed reality with unusual inevitability. Equations whose form carried the sense that nature had been forced into its own cleanest statement. His search for a relativistic quantum equation of the electron was exactly that kind of effort. The existing quantum descriptions worked well enough in limited domains, but they treated time and space asymmetrically in ways relativity did not tolerate gracefully. What was needed was not just a patch, it was a framework in which the electron could be described consistently as both a quantum object and a relativistic one. And when Dirac found that framework, it did more than repair a technical inconsistency. It widened reality. That is one of the enduring shocks of theoretical physics at its highest level. Sometimes an equation, written to solve one problem, returns with more world than was put into it. A structure designed to make two theories coexist begins yielding entities, symmetries, and possibilities no one set out to request. The mathematics does not merely obey, it surprises. Dirac's equation had that quality. At one level, its achievement was straightforward to state and extraordinarily difficult to accomplish. It gave a description of the electron compatible with both quantum mechanics and special relativity. It accounted for properties of the electron with a precision and grace that made it immediately powerful. Spin, which had entered the theory in a somewhat ad hoc way, emerged naturally from the formalism. The equation seemed, in the best sense, smarter than a mere fit to data. It carried hidden reserves, but those reserves came with a disturbance. The structure of the equation implied solutions corresponding not only to the familiar electron states physicists expected, but to another sector as well, states that looked, at first, deeply problematic. In simple language, the mathematics seemed to allow energies of the wrong sign. The result was not a minor nuisance. It threatened instability. If these states were interpreted crudely, one could imagine electrons cascading downward without limit into ever lower energies, a physical catastrophe clearly not occurring in the world. Dirac's response was not to discard the equation in panic. He did what the strongest theorists sometimes do when mathematics becomes disobedient. He treated the disobedience as evidence. That required nerve. Because it is always tempting to assume that the unexpected part of an elegant equation is the mistake. The human mind wants success to come filtered through familiarity. It is comfortable when the mathematics confirms what experience already knows how to name. Dirac was willing to entertain a more dangerous possibility, that the unfamiliar terms were not noise, but ontology, that nature was larger than the expectation used to summon it. His resolution evolved, and some of its original interpretive language would later be superseded, but the core insights survived with historic force. Alongside the electron, there should exist a corresponding particle of opposite charge and equal mass, a mirror counterpart. Not merely a mathematical fiction, but a real possibility in the structure of the world. Antimatter entered physics not first as an experimental oddity, but as an unwanted symmetry in an equation too good to ignore. That matters enormously for the vacuum, because it changes the meaning of absence at a stroke. Until now, the quantum vacuum had become restless in a fairly abstract sense. The ground state was not trivial, fields could not be thought away. Fluctuation-like behavior had entered the conceptual picture, but Dirac's work gave that picture a new kind of architecture. If matter has opposites built into the underlying formalism, then the vacuum no longer sits beneath the world as a neutral, empty bed. It becomes a place defined against a doubled possibility. The universe is not just built to contain particles, it is built to contain counterparts. You can feel the pressure of that change by imagining the simplest object of ordinary matter, the electron, losing its singular privilege. For every electron, the theory points toward a positron. For charge, an opposite charge. For a given particle content, a mirrored inversion in crucial properties. The old world of things now acquires anti-things, not as fantasy, but as a consequence of taking the equations seriously enough to let them finish their sentence. That mirrored structure is one of the coldest and most beautiful turns in 20th century physics. It says that the world is not merely populated, it is symmetric in ways common sense never asked for. The electron was not alone. Matter itself had a kind of reflection written into the mathematics. And reflections have consequences, because if particle and antiparticle meet, they can annihilate. Their mass can be converted into radiation, not dissolve in some vague poetic sense, but undergo a precise transformation constrained by conservation laws and described with unforgiving accuracy. Matter and antimatter are not simply different species that pass each other indifferently. They carry, in their relationship, the possibility of mutual erasure into energy. Now the vacuum becomes much more dangerous. Not yet, because pairs are literally bursting visibly out of empty rooms like sparks. That is still too crude. But because the formal world beneath the visible has acquired a mechanism by which the ground state can be associated with particle-antiparticle structure in a way classical emptiness never could have supported. The vacuum is no longer merely a low-activity background in which fields exist. It becomes the reference state against which excitations, including mirrored excitations, are defined. The possibility space has thickened. And with that, one of the oldest intuitions about nothing finally begins to fail beyond repair. The old intuition said that emptiness was what remained after the world's contents were removed. It imagined the void as the result of subtraction. But subtraction no longer reaches the bottom once the world is described by quantum fields with relativistic symmetry. Take away ordinary matter, and you do not arrive at a simple blank. You arrive at a structured baseline from which paired possibilities can be meaningfully described. The vacuum is not under the world like a bare floor. It is woven into the very language by which the world's excitations are counted. This is why Dirac belongs at the centre of the narrative rather than at its margins. He is not just the discoverer of antimatter in some isolated heroic sense. He is one of the figures through whom emptiness loses its last naive form. His equation makes it impossible to think of the vacuum as merely where particles are not. The vacuum becomes implicated in the logic of what particles are, what opposites they require, and how existence and annihilation can be paired inside one mathematical framework. There is also a more intimate reason his role matters. Dirac shows that the deepest fractures in intuition are not always forced by direct sensory encounter. Sometimes they are forced by coherence, by the refusal to allow two successful theories to remain incompatible, by the discipline of insisting that reality, whatever else it may be, cannot answer to mutually contradictory fundamental descriptions in the same domain. When that discipline is pursued far enough, the world answers with things no one was emotionally prepared to want. The positron was eventually observed in cosmic ray experiments. The mirror was real. That confirmation gave the equation retrospective inevitability, but it must not erase the strangeness of the original step. Before detection, the idea stood exposed and severe. If the mathematics is right, then matter has an opposite. If matter has an opposite, then the vacuum cannot be imagined as a mere passive blank between actual objects. It belongs to a reality whose baseline already contains the formal possibility of paired emergence and paired cancellation. The air is gone. The ether is gone. Classical stillness is gone. And now singularity is gone too. Matter no longer stands alone against emptiness. It comes shadowed by its inverse, written into the structure deeply enough that the vacuum itself must be thought in relation to this doubled architecture. The world is not merely stranger than it looked. It is more symmetrical and less comforting. Because once the equations allow matter and antimatter as matched possibilities, the next question is no longer whether emptiness can host hidden structure. That is already decided. The next question is what that structure actually does when the vacuum is treated as the quantum ground state of fields rather than a philosophical absence. At that point, the old language of nothing has almost run out. What comes next will finish it. Because the vacuum is about to stop being merely a state over which theory casts a shadow and start leaving fingerprints inside the atom itself. Because once the vacuum is no longer treated as a blank, it can begin to act, not in the theatrical sense, not as a visible storm churning in empty rooms. The danger here is always the same, to replace one oversimplification with another. The quantum vacuum is not a hidden gas of tiny marbles flickering on and off like sparks in a dark chamber. If the language becomes too pictorial, it starts lying. But neither is the vacuum inert. That is the line that now has to be crossed carefully. Dirac's equation and the development of relativistic quantum theory did not merely add antimatter to a pre-existing world, they changed what counted as baseline. Once particles are understood as excitations of underlying fields, and once those fields admit a ground state richer than classical nothingness, emptiness itself becomes physically consequential. The vacuum is no longer just the place where detectable particles are absent. It is the state with respect to which particles, antiparticles, and their interactions are defined. That distinction sounds technical until you feel its implication. Classically, a stage remains unchanged whether actors enter it or not. It simply waits. But the quantum vacuum is not a stage in that sense. It is more like the lowest tensioned condition of an instrument, the stillest state possible perhaps, but not a dead one. A string at rest is not non-existent. It retains the structure from which vibration can emerge. The analogy is incomplete, but it points in the right direction. The vacuum is not no world. It is the ground condition of a world built from fields. And if the fields are there, their structure does not disappear merely because you have removed ordinary particles from a region of space. This is where the language of particle-antiparticle pairs enters, and where one has to be honest about both its power and its limits. In popular explanations, the vacuum is often described as constantly spawning virtual particles that pop into existence and then vanish. That picture is useful up to a point, because it captures the fact that the vacuum in quantum field theory is not empty in the classical sense, and that interactions can be fruitfully described in terms of transient internal processes. But taken too literally, it becomes misleading. Virtual particles are not ordinary particles hiding just below visibility, nor are they tiny physical objects appearing in exactly the same way experimentally detected particles do. They are part of the calculational architecture of the theory, manifestations in the formalism of how fields interact and fluctuate. Still, the picture persists for a reason, because it gives intuition at least a partial handle on something real. The vacuum can contribute to physical processes as though transient pair structures matter. Particle and antiparticle possibilities do not merely sit as abstract options on a blackboard. They alter the behavior of the world. They enter scattering amplitudes. They modify energy levels. They screen charges. They leave measurable traces. This is why the vacuum starts to feel less like absence and more like suppressed activity. Not visible activity, not coarse activity, but lawful, encoded, unavoidable contribution. Imagine for a moment an electron moving through what common sense would call empty space. In the classical picture, that electron simply exists against a neutral background. It carries its charge, its mass, its motion, and the vacuum contributes nothing except room. In the quantum field picture, that simplicity evaporates. The electron is no longer isolated against emptiness, like a pebble in airless darkness. It is immersed in a field-theoretic world in which the vacuum itself participates in how charge and interaction are manifested. One way to think about this, cautiously, is that the vacuum around a charged particle is not indifferent to the charge. The surrounding quantum fields respond. In the formal language, the vacuum can become polarized. Pair-like contributions of opposite charges around the electron affect how its electric influence is distributed. The bare object of naive theory is not what experiments directly encounter. It is dressed, in part, by the vacuum. That word is worth dwelling on. Dressed. It tells you that emptiness is no longer naked space. Even in the absence of ordinary matter, the quantum vacuum participates in the effective appearance of particles. A measured electron is not simply an isolated nugget bearing timeless, untouched properties. It exists inside a relational structure where the vacuum modifies what the particle effectively is for the purposes of observation and interaction. This is a profound wound to the old idea of nothing, because now emptiness is not only the condition in which particles move, it helps determine how they move and what we mean by their observable properties. The vacuum has crossed from backdrop into agency. Again, not agency in the human sense, not intention, not action by will, agency in the hard physical sense of consequence. The story becomes even sharper when you remember what annihilation means in this framework. Particle and antiparticle are not merely opposites in an abstract registry. Their coexistence opens a channel through which mass-energy relationships can be transformed with exactness. When an electron and positron meet, they can annihilate into photons. The world can trade one form of excitation for another while respecting conservation laws. That possibility is not a decorative oddity. It is built into the architecture of the theory. So when the vacuum is described as containing pair-like fluctuation structure in the formal sense, the logic is no longer mystical at all. It follows from the fact that the world's baseline must be compatible with a field theory whose excitations come in these mirrored forms. The vacuum is not generating arbitrary spectacle. It is reflecting the symmetry and interaction structure of the fields themselves. And once you accept that, the old term empty space becomes almost embarrassingly crude. Space is not full of little hidden objects in the old mechanical way, but neither is it stripped to literal non-being. It is the lowest energy condition of a set of fields whose existence remains even when no ordinary particles are present. That condition can affect measurable phenomena. It can shift probabilities. It can alter interactions. It can behave, under analysis, as though pair structure contributes to what occurs. The void is not empty of events. It is empty of permanence. That is a better sentence than the common slogan, because it preserves the central truth without pretending the vacuum is an ordinary swarm. What the vacuum lacks are stable, directly detectable particle excitations. What it does not lack is structure. Not lack is consequence. Not lack is the latent architecture from which particles, interactions, and measurable modifications arise. You can feel how far this is now from the original box. At the beginning, the problem was almost childlike in form. Remove everything. What remains? The naive answer was supposed to be nothing. Then came air, then pressure, then the ether, then its death, then relativity, then quantum uncertainty, then Dirac's doubling of matter. Each step removed one simplification. But now the cumulative effect is harder than any individual revelation. The operation of removing everything has itself become unstable, because everything was never just particles. It was never just visible contents. The fields remain, their ground state remains, their lawful fluctuations remain, their effect on the world remains. So the vacuum is no longer what you get after the universe is taken away. It is one of the ways the universe exists. That line matters because it prepares the next move. Up to now, much of the argument has remained conceptual. The vacuum is being reclassified, re-understood, rebuilt inside theory. But theory can only carry the story so far before it incurs a demand. If the vacuum is genuinely structured in the ways quantum field theory suggests, then it must do more than sit elegantly inside mathematics. It must disturb something measurable. It must leave a wound in experiment. And the wound it leaves is exquisitely small. Not on cosmic scales first. Not in some flamboyant astronomical event. In a single atom. This is one of the most beautiful turns in the whole story, because it compresses the entire descent into something minute. The atmosphere had required columns of mercury. The ether had required an interferometer. Relativity had required a reconstruction of space-time. Quantum theory had reconstructed stillness. Dirac had doubled matter, and now all of that pressure is about to be brought to bear on the energy levels of a hydrogen atom. That is where the vacuum will finally stop sounding philosophical and start becoming undeniable. Because if the vacuum were truly empty in the classical sense, the atom should obey one pattern. If the vacuum is physically active in the quantum field sense, the pattern shifts. And that shift, absurdly tiny though it is, can be measured. The old void had already lost its innocence. Now it is about to lose its invisibility in one of the smallest measurements human beings have ever managed to trust. This is where the vacuum stops being protected by abstraction. Up to this point, one could still tell oneself that the strange language surrounding empty space belonged mostly to theory, to equations, symmetries, formal structures, and the unavoidable weirdness of the quantum world. Serious, yes. Beautiful, perhaps, but still buffered from ordinary belief by the distance between mathematics and touch. The Lamb shift ended that buffer. What Willis Lamb and others helped make visible was not some grand theatrical eruption of the vacuum, but a minute discrepancy in the energy structure of the hydrogen atom. A discrepancy that classical Dirac theory, elegant as it was, did not fully predict on its own. The effect was tiny, appallingly tiny. But that was precisely the point. If the vacuum were truly inert in the old sense, the atom should sit in one clean pattern. If the quantum vacuum contributes through the structure of the fields, that pattern should be nudged. And it was. The atom is a perfect place for this confrontation, because it sits at the boundary between apparent simplicity and hidden depth. Hydrogen, in its most familiar form, is almost offensively minimal. One proton, one electron. If any atom should have been conceptually exhausted by theory, this one would seem a good candidate. And yet, even here, the world refused to be finished. The electron did not simply occupy energy levels as though the vacuum around it were a dead backdrop. Something in the surrounding quantum structure altered the details. That is the wound. Not a failure of physics, but a refinement of what physics had to mean. To see why this matters, forget for a moment the common image of the atom as a tiny solar system. Even as a pedagogical sketch, it quickly becomes dangerous. The electron in quantum mechanics is not a little bead circling a nucleus along a classical track. It is described by a quantum state, a wave function, with allowed energy levels determined by the structure of the system. Certain states that naive theory would treat as having the same energy are, in the real world, ever so slightly split. Why? Because the vacuum is not indifferent. In quantum electrodynamics, the quantum field theory of light and charged matter, the electron does not live in isolation from the electromagnetic field, even in what we loosely call empty space. The vacuum can contribute radiative corrections. The electron's interaction with the fluctuating quantum electromagnetic field modifies the effective energy structure of the atom. The result is a tiny shift in the levels. Tiny, but not optional. Tiny, but measurable. This is what makes the Lamb shift so beautiful. It is not merely a technical correction in an advanced theory. It is experimental evidence that the vacuum is physically consequential. The empty space in and around the atom is not a passive absence through which nothing relevant occurs. The ground state of the field, with all its quantum structure, changes what the atom is allowed to be. Nothing leaves a measurable bruise. That is the sentence hidden inside the experiment. And what a bruise it is. The shift is extraordinarily small, so small that any sensible person outside physics would probably assume it belonged to the realm of irrelevance. But reality is not graded by human scale. Some of the most important truths in science arrive as discrepancies so minute that only a civilization obsessed with precision would bother to pursue them. A tiny correction, if it is lawful and repeatable, can reveal more about the architecture of the universe than vast spectacles ever do. Lamb's work did exactly that. By carefully probing the energy transitions in hydrogen, he exposed the fact that the vacuum contributes to the atom's behavior. The exact numbers matter to specialists. The broader significance matters to everyone. The atom does not simply sit inside emptiness. It sits inside a quantum vacuum whose structure modifies what can occur. The old classical divide between the system and the empty space around the system breaks down. Empty space is part of the system. That is one of the most destabilizing themes in all of modern physics. We want to believe there is a clean difference between an object and the nothing around it. We want the world's entities to possess their properties in themselves, with the void serving only as room. The vacuum keeps defeating that desire. First it refused to be impossible, then it refused to be full of a classical medium, then it refused to be perfectly still. Now it refuses to be irrelevant. And the precision with which the theory matches experiment only deepens the shock. Quantum electrodynamics is among the most accurate frameworks ever constructed. Its predictions, when worked through carefully, agree with measurements to astonishing precision. This is not a vague philosophical resonance between idea and observation, it is a brutally quantitative success. The vacuum's contribution is not an indulgent metaphor layered onto nature afterward. It is part of the machinery by which nature actually computes itself. That sentence is dangerous if misheard, so it is worth stating more soberly. We do not literally mean the universe is running equations. We mean that the mathematical structure that treats the quantum vacuum as physically active yields predictions whose agreement with experiment is almost unnervingly exact. The world behaves as though the vacuum has the kind of structured consequence the theory assigns to it. And once that happens, the conceptual status of emptiness is permanently changed. You cannot go back to the box. Or rather, you can return to it, but never innocently. The sealed chamber that once seemed merely evacuated now sits inside a much harder world. Remove the gas, remove the contaminants, remove the ordinary particles if you can. The region does not become philosophically blank. It becomes a quantum vacuum. A physical state whose structure is quiet enough to hide from casual experience, but not quiet enough to avoid influencing atoms themselves. This is the point where the narrative can widen again, because once the vacuum has demonstrated its power inside the atom, it becomes impossible not to ask a much larger question. If quantum fluctuations can leave fingerprints on something as small as hydrogen, what happens when the entire early universe is small enough for quantum structure to matter everywhere at once. That is not a rhetorical escalation. It is a real one. The atom gave us a local bruise. Cosmology now asks whether the whole visible universe carries scars of the same underlying restlessness. To feel the force of that leap, it helps to remember how violently the scale changes. In the lamp shift, we are dealing with one of the smallest bound systems in nature and one of the most delicate corrections in theoretical physics. It is microscopic, intimate, almost absurdly fine. But the early universe was once smaller than atoms, denser than ordinary imagination can tolerate, and governed by the same quantum laws. If the vacuum is physically structured there, as the theory insists, then the largest objects in existence may owe part of their origin to the same deep framework that nudges an electron's allowed energies. That is one of the great inversions in science. We tend to think of the small as negligible and the large as definitive. But in modern physics, the large is often a stretched, amplified, fossilized consequence of what happened at scales too small and too early for common sense to survive. The cosmic can be the expanded residue of the microscopic. The architecture of galaxies can descend, in part, from fluctuations so tiny that they would once have seemed beneath significance altogether. So the vacuum is not merely winning the argument on multiple fronts. It is changing the scale at which the argument matters. Empty space is no longer a niche puzzle about chambers, tubes, and laboratory curiosities. It is now implicated in atomic physics and poised to enter cosmology. The same reclassification that made the vacuum physically consequential in one atom threatens to make it architecturally consequential for the whole universe. There is a severe beauty in that movement. The old question was childlike. What is inside an empty box? The mature question is colder. What is the lowest energy state of reality, and how much of existence inherits its structure from that state? That second question does not merely ask what the vacuum is. It asks what the vacuum has done, and the answer, if modern cosmology is even partly right, is almost unbearable in scale. Because the quantum vacuum does not just disturb atoms. It may have written itself into the sky. This is where the descent becomes difficult to hold in one mind at once, because the scales begin to tear apart ordinary intuition. The vacuum, which first appeared as a problem inside a box, then as a subtle disturbance inside an atom, now steps onto the largest stage available. Not metaphorically, cosmologically, the key to the transition is not grandeur, it is size. There was a time when the entire observable universe was compressed into a state so hot, so dense, and so small that the distinction between particle physics and cosmology had not yet opened into separate disciplines. In that regime, the universe was not a vast arena containing quantum events here and there. It was, itself, a quantum system in violent expansion, which means the vacuum and the fluctuations associated with the quantum fields were not peripheral details. They were part of the deep initial texture from which everything later grew. This is one of the most elegant and unsettling ideas in modern science, that the largest visible structures in existence may descend, in part, from microscopic irregularities embedded in the vacuum-like state of the early universe, and then stretched to astronomical scales by cosmic expansion. The general picture most widely used to explain this is inflation. That word should be handled carefully, because it names a powerful framework, not a closed and complete final theory. Inflation, in its broad form, proposes that the very early universe underwent a brief period of extraordinarily rapid accelerated expansion. Different models implement that idea in different ways, and some details remain open to debate. But the overall framework has been influential because it helps explain several otherwise puzzling large-scale features of the cosmos, and, crucially here, because it offers a mechanism by which microscopic quantum fluctuations could be magnified into macroscopic structure. This is where the vacuum stops sounding like a local technicality and starts sounding like authorship. Imagine a region of the early universe in a very high-energy state, often modelled through one or more fields whose dynamics drive rapid expansion. Even if the state is relatively smooth on average, quantum theory does not permit perfect classical smoothness. There are fluctuations, tiny departures from exact uniformity. Not bumps in matter in the everyday sense, because the universe at that stage is not yet a settled sea of stars and gas and planets, more like minute irregularities in the primordial field configuration and energy density, small enough to be microscopic, real enough to matter if expansion is violent enough to stretch them. And that stretching is the crucial move. Under ordinary conditions, fluctuations at tiny scales would remain tiny. They would average out, disappear into irrelevance, or simply stay confined to the microscopic domain. But if space itself expands rapidly enough, those tiny irregularities can be pulled outward, frozen into larger scale patterns, and later re-enter cosmic history as seeds for structure. The largest arrangements of matter in the universe would then not begin as grand shapes. They would begin as amplified imprecision. That sentence is almost too strange to trust, which is usually a sign that science has reached somewhere worth slowing down. Amplified imprecision. Not chaos. Not randomness without law. And not a cosmic accident in the cheap sense. A lawful transformation in which tiny quantum deviations in the early state become the scaffolding for later gravitational clustering. This is the deeper meaning of the claim that the vacuum may have written itself into the sky. We do not mean the vacuum as philosophical nothingness somehow decided to create galaxies. We mean that the quantum structure of the early universe, the fluctuations permitted by the fields and their state, may have left imprints that later gravity turned into stars, galaxies, and the large-scale web of matter stretching across the cosmos. The evidence for this is not theatrical. It comes in one of the quietest and most profound images humans have ever extracted from nature, the cosmic microwave background. The microwave background is often called the afterglow of the Big Bang, which is serviceable language as long as it is not taken too loosely. More precisely, it is relic radiation from a time when the universe had cooled enough for light to decouple from matter and begin travelling freely across space. What satellites such as COBE, WMAP, and Planck revealed with increasing precision was that this radiation is astonishingly uniform, but not perfectly so. Its temperature varies across the sky by tiny amounts, minute anisotropies, faint differences, almost nothing. And almost nothing is exactly the scale on which the story of the vacuum likes to become decisive. Those tiny differences are not visual decoration, they are the early map of unevenness, the places where the primordial universe was ever so slightly denser or rarer than the mean. Over immense spans of time, gravity would amplify those departures. Slight overdensities would attract more matter, structure would grow, galaxies would gather, clusters would form. The visible universe would acquire shape because the early universe was not perfectly smooth. The haunting possibility is that this primordial unevenness traces back, in a deep sense, to quantum fluctuations stretched outward by inflationary expansion. That claim is not a poet's inflation of the science, it is the science at its most severe and beautiful. The largest patterns we can observe may be enlarged relics of microscopic quantum restlessness. A galaxy, in that picture, is not merely an island of stars formed from cooling gas. It is a magnified consequence of an early departure from exact symmetry. A cluster of galaxies is not just a vast object. It is a fossil of a fluctuation once so small that the language of ordinary material causation becomes almost useless. That is the scale inversion at the heart of the modern vacuum story. The vacuum does not only matter in the empty box. It does not only matter in the spectral precision of hydrogen. It may matter in the existence of cosmic structure itself. The sky may preserve, at enormous scales, the stretched memory of the quantum world. Nothing, in that case, did not merely surround everything. It helped pattern everything. This is also the point where honesty becomes important, because cosmology is powerful, but not omniscient. Inflation remains a leading explanatory framework, not a finished final answer. There are multiple inflationary models, open questions about the underlying fields and mechanisms, unresolved issues about initial conditions, and serious ongoing efforts to test competing ideas against observation. One should not pretend that every detail is settled, but one can say responsibly that the connection between early universe quantum fluctuations and later structure formation is one of the most important and successful conceptual bridges in modern cosmology. And even in its cautious form, the bridge is enough to transform the meaning of emptiness. The vacuum is no longer merely a condition we produce in chambers, no longer merely a formal ground state with tricky quantum behavior, no longer merely an active participant in atomic physics. It becomes part of the story of why the universe is not smooth and dead, why there are galaxies instead of a bland, featureless distribution, why matter gathered into islands, why the night sky has shape. There is something almost cruel about that revelation, because it turns the old intuition inside out completely. The intuition said emptiness is what remains when structure is removed. The modern picture suggests that the quantum structure associated with the vacuum may be part of why large-scale structure exists at all. The void does not simply receive the universe, it helps script its asymmetries. That line should be held with care, because again, one must not collapse metaphor into literal mechanism. The vacuum is not an author with intention. The laws do not dream galaxies into being. But lawful fluctuations in the early quantum state, amplified by expansion and gravity, concede the structures from which all later visible complexity emerges. In that sober sense, the vacuum is not merely passive, it is generative. And that pushes the emotional weight of the story into a new register. At the beginning, nothing seemed philosophically elusive. Then it became experimentally slippery. Then it became quantum mechanically unstable. Now it becomes cosmologically fertile. The emptiness we expected to be a dead remainder begins to look like one of the preconditions for visible order. There is no comfort left for classical intuition here. The world is not built from solid things dropped into a blank. The blank itself was never blank. It carried, at minimum, the lawful capacity for disturbance, and in the earliest moments, that disturbance may have been enough to prevent perfect uniformity, enough to give gravity something to work on, enough to make later complexity possible, enough that our own galaxy, our sun, the Earth, and every living body may trace part of their deep ancestry, not just to stars or atoms, but to tiny quantum departures from smoothness in the early state of the universe. This is the point where the vacuum stops being merely strange and starts becoming intimate. Because once you understand the logic, the night sky is no longer just full of objects, it becomes full of amplified fluctuations, ancient overdensities, preserved accidents of exact smoothness that never quite happened. The Milky Way ceases to be just a collection of stars and becomes, in part, a grown irregularity, a swelling of ancient imbalance. The visible universe is not simply matter filling emptiness, it is form emerging from a baseline that never managed to stay perfectly flat. And even that is not the end of the descent, because structure is only one inheritance from the early vacuum. There is another, narrower, crueler question waiting beneath it. If the early universe could give rise to matter and antimatter in nearly equal abundance, and if the laws allowed them to annihilate one another with almost perfect efficiency, then why is there anything left at all? Why did the cancellation fail? Why is the universe not a smooth bath of radiation, with no stars, no planets, no bodies, asking what nothing is? By the time we reach that question, the old box has become almost unrecognizable. We were trying to discover what remains when everything is removed. Now we have to ask why everything was not removed in the first place. Because if the early universe truly carried the symmetries modern physics attributes to it, if matter and antimatter were produced in nearly equal abundance as the hot primordial state cooled, then the most natural expectation is not a cosmos full of galaxies. It is a near total cancellation. That cancellation is not speculative drama, it is ordinary consequence. Matter and antimatter do not coexist comfortably when brought together. They annihilate into radiation with astonishing efficiency. Put enough of both into the same young universe, and almost all of each should disappear into light. The result should be a cosmos whose dominant inheritance is not structure made of matter, but energy released by mutual erasure. And in one sense, that is exactly what happened. The early universe was a furnace of interactions, collisions, pair production, annihilation, and thermal equilibrium so extreme that our ordinary categories barely survive translation into it. Matter and antimatter were not rare isolated curiosities. They were part of the general plasma of the world, and as the universe expanded and cooled, annihilation did proceed with overwhelming thoroughness. Vast numbers of particles and antiparticles disappeared into radiation, but not perfectly. That imperfection is one of the most consequential asymmetries in existence. Somehow, for roughly every enormous number of annihilating particle-antiparticle pairs, a tiny excess of matter remained. Tiny by proportion, catastrophic by consequence. Because the stars, planets, oceans, cells, nerves and questioning minds of the later universe were built from that residue. Everything familiar is not the primary outcome of the early universe. It is the leftover. We are not the product of symmetry. We are the product of its failure. That is a severe way of putting it, but it is closer to the emotional truth of the physics than more comforting language tends to be. Matter did not simply fill the cosmos by default. It survived by a margin so narrow that, had the balance gone the other way or closed more completely, the visible structures of the universe might never have formed at all. There would still have been law, still have been radiation, still have been space-time evolving, but perhaps no chemistry, no stars of the familiar kind, no planets, no bodies, nothing dense enough and stable enough to become us. So the question is brutal and unavoidable. Why was there a surplus at all? This is the baryon asymmetry problem in broad outline, though the full story reaches into several related asymmetries and beyond the currently complete standard model of particle physics. To explain why matter came to dominate over antimatter, physics requires more than poetic astonishment. It requires mechanisms that satisfy very specific conditions, processes that violate certain symmetries, occur out of thermal equilibrium, and allow the universe to distinguish, however slightly, between matter and antimatter in its evolution. Some of those ingredients are known in limited forms, some are established in part, but the full quantitative explanation for the observed cosmic excess remains unresolved. That uncertainty matters because it keeps the ending honest. We do not know the complete story. What we do know is enough to rearrange the feeling of existence. The radiation filling the universe today, most quietly visible in the microwave background, bears witness to the vast annihilations that occurred. The matter around us bears witness to the fact that the annihilation was not exact. The stars are not simply what the Big Bang made. In a very real sense, they are what escaped. This is where the story of the vacuum acquires its most intimate edge. At first, empty space seemed to be the opposite of everything that matters. Then the vacuum became the ground state of fields, then a source of measurable effects, then a contributor to the early structure of the cosmos. Now it stands indirectly behind a harder realization. The world we inhabit is not the inevitable positive content of reality. It is the thin surviving imbalance after a near-complete cancellation. Everything substantial may be debris. Not debris in the messy everyday sense, but residue. The remnant after an almost perfect symmetry burned itself away. That thought is hard to absorb, because the human world feels dense, stubborn, overfull. Cities, mountains, oceans, bodies, memory, all of it presses on the senses with the authority of permanence. But cosmologically, this authority is misleading. The matter composing familiar structures is a minute leftover relative to the energy scales and cancellations that dominated the early universe. Our apparent fullness is local. The underlying story is one of overwhelming erasure and narrow survival. In that sense, the old intuition about nothing undergoes one last reversal. We began by imagining nothing as what might remain if the contents of the universe were removed. But now the better question is whether the contents we know were ever more than a tiny, non-cancelled excess to begin with. Existence does not stand over against emptiness as a triumphant positive mass. It flickers out of near balance. It survives inside an asymmetry so fine that its cause is still only partly understood. That should change the emotional temperature of the sky. Look at a galaxy, and common sense says abundance. Look again through the physics, and the galaxy becomes an improbable residue. Matter that was not annihilated. Structure that grew from primordial unevenness. Stars assembled from a tiny excess left behind after a vast destruction. The visible universe becomes less like a monument and more like a remainder. A remainder can still be magnificent, but its magnificence is colder, and it brings the vacuum back into focus in a new way. Because the vacuum, by the time the story reaches this point, is no longer merely a strange background state. It is implicated in the early high-energy conditions from which matter, antimatter, radiation, and structure emerged. It is part of the framework in which the asymmetry problem is posed, not because nothing itself straightforwardly explains why matter won, we do not responsibly know that, but because once the vacuum is understood as the ground state of quantum fields, the origin story of everything familiar is no longer a simple march from blank absence to full presence. It is a passage through fields, fluctuations, symmetries, symmetry breaking, annihilations, and leftovers. The old language of creation from nothing becomes dangerously loose here, and it is worth resisting that looseness. Modern cosmology does not license the casual claim that the universe literally emerged from philosophical nothingness in any settled, final sense. Some models describe quantum tunneling from certain vacuum-like states. Some treat the very notion of before as unstable or meaningless near the origin. Some leave the question open altogether. What is clear is that the vacuum of physics is not identical to the metaphysical nothingness of pure absence. Confusing those two has generated endless heat and very little clarity. And yet the temptation remains, because the emotional shape of the problem is so powerful. We want a clean contrast between being and non-being, a line where the universe either is or is not. The science keeps dissolving that line into something more severe. The relevant baseline is not philosophical emptiness, but physical state. The relevant drama is not being versus nothing in the abstract, but how specific lawful conditions gave rise to the tiny, durable excess from which the visible universe was built. This does not make the story smaller. It makes it more exact. And exactness, here, is more haunting than rhetoric. That is why the final movement of the script has to return to the box. Not because the box can now be answered simply, but because it can now be seen properly. At the start, the box seemed like a child's challenge to philosophy. Remove everything and ask what is left. By now, the box has become almost unbearable as an image, because nothing in it is simple anymore. Remove the air and you confront pressure. Remove the medium and light still crosses. Remove the particles and fields remain. Demand stillness and fluctuations survive. Follow those fluctuations forward and the sky remembers them. Follow matter back and it is residue of a near annihilation. The box was never asking about emptiness alone. It was asking whether reality has a true blank layer beneath appearance. And the answer, as far as physics has been able to force one, is increasingly severe. Not in the way intuition hoped. What lies beneath appearance is not a simple void. It is a structured minimum, a lawful ground, a state whose quietness is real but not absolute, whose influence is measurable, whose early irregularities may have seeded the universe, and whose relation to the survival of matter remains entangled with some of the deepest open problems in fundamental physics. That is why the vacuum is so unsettling, not because it is merely strange, but because it erodes the comfort of final subtraction. It denies us the fantasy that if we take enough away, we will eventually arrive at a conceptually innocent nothing. There may be no innocence at the bottom, only deeper law. And that law has already done enough to leave us here. Fragile, temporary concentrations of leftover matter, living inside a universe that came perilously close to being all cancellation and no witness. Which means the final question is no longer, what is nothing? It is something colder. What kind of world produces a remainder like us? From a baseline that never stopped being more than empty, a world in which the deepest layer we can currently describe is not a blank beneath things, but a physical state beneath our intuitions. That is the final turn, because by now the old question, what is nothing, has almost dissolved under the pressure of everything we had to learn in order to ask it honestly. The answer did not become cleaner as physics advanced. It became more exact and less forgiving. Every time we tried to strip reality down to absence, some deeper structure remained. First air, then fields, then quantum uncertainty, then the vacuum state itself, with its measurable consequences, its role in atomic physics, its possible imprint on the early universe, its unresolved relation to cosmic acceleration, its entanglement with the survival of matter. The journey did not reveal that nothing is full in some sentimental slogan-like way. It revealed that what we call nothing was never a primitive category of physics to begin with. That is harder and better. Human language treats nothing as if it was simple, because language evolved for tables and storms and empty rooms. It evolved to navigate medium-sized reality, where subtraction works well enough and absence can be handled as a practical contrast. No food on the plate, no one in the house, no water in the cup. At that scale, nothing is useful. It tells us what matters has gone missing. But the universe is under no obligation to preserve the categories that made us competent apes. At deeper scales, there is no guarantee that absence will remain a pure condition. No guarantee that removing particles removes physicality. No guarantee that the background stops contributing just because familiar matter is gone. Physics does not ask what our language wants nothing to mean. It asks what state the world can actually occupy when excitations are minimized, when ordinary contents are removed, when the fields are in their lowest accessible configuration. And the answer is not philosophical non-being. It is the vacuum, a word that sounds empty only because our instincts are old. This is why the box from the beginning has changed so completely. At first it seemed like a straightforward challenge. Seal a region of space, remove everything, ask what remains. The elegance of the image was that it appeared to promise a final subtraction, as if reality had some last clean layer waiting patiently beneath all clutter. But the box does not give us a clean edge between being and non-being. It gives us a confrontation with the fact that the world may not be built from that opposition at all. Inside the box, once the air is gone, pressure has already taught you that the invisible was physical. Once the medium is gone, light has already taught you that propagation does not need the mechanical carrier intuition demanded. Once the particles are gone, quantum field theory has already taught you that the vacuum is not equivalent to literal nothingness. Once you look closely enough, the atom teaches you that this vacuum is not inert. Once you widen far enough, cosmology suggests that its early fluctuations may have helped script the structure of the sky. And once you trace matter itself back toward the furnace of the young universe, you find that the solid world was never the obvious default. It was the thin residue of an almost complete cancellation. By the end, the box is no longer an object. It is a ruin of intuition. That is the perception shift the whole descent was always aiming for, not the cheap thrill of calling emptiness mysterious, not the vague comfort of saying everything is connected. Something colder, more disciplined, more destabilizing. The realization that reality does not bottom out where common sense expects. We expect the fundamental layer to be simpler than appearances, more stripped down, more easily named. We imagine that depth means reduction, and reduction means cleanliness. Remove the noise, remove the complication, remove the visible furniture of the world, and the final truth will stand there in austere simplicity, a kind of metaphysical bedrock. Sometimes science does move that way, but not here. Here, the deeper layer is not less strange than the surface. It is stranger in a more lawful way, less anthropocentric, less imageable, less willing to let our old oppositions survive intact. The vacuum is a perfect example of that. It is not the erasure of the universe. It is one of the forms the universe takes when it is stripped below the level our senses were designed to understand. That is why the history mattered. Not because it gave us a parade of discoveries, but because each stage removed a different false comfort. Aristotle lost the comfort that emptiness is impossible. Torricelli and Pascal lost the comfort that the atmosphere is nothing. Michelson and Morley lost the comfort that light must ride on a hidden medium. Quantum mechanics lost the comfort that the ground floor of reality is exact in the classical sense. Dirac lost the comfort that matter stands alone. Quantum electrodynamics lost the comfort that the vacuum can be ignored. Cosmology lost the comfort that structure begins large. And we lose, at the end of all this, the comfort that existence sits cleanly over against absence. That is the residue the script has to leave behind. Not confusion, clarity. But a clarity with edges, because once you see the vacuum properly, The familiar world becomes harder to take at face value. Solidity starts to look like negotiated force. Space starts to look less like a container and more like a regime. Matter starts to look like a temporary excitation in a wider field-structured reality. The night sky starts to look like amplified irregularity. Even survival itself, the fact that there is something here, rather than an almost exact wash of radiation, starts to look like the product of asymmetry so slight that physics is still trying to account for it completely. That does not make the world unreal. It makes it less intuitive than our bodies promised. And perhaps that is one of the deepest functions of science at its best. Not merely to add knowledge, but to discipline perception. To break the lazy alliance between what feels obvious and what is true. To show that the universe is lawful without being psychologically accommodating. To reveal that deeper understanding does not always simplify reality. Often it removes the wrong simplicity and leaves you facing something harsher, cleaner, and more beautiful than comfort would have allowed. The vacuum is exactly that kind of revelation. It is severe because it denies the fantasy of pure absence. It is beautiful because it does so through structure rather than mystification. It is haunting because it sits so close to everyday language while meaning something so much deeper than language first intended. When people say empty space, they usually mean a lack of visible things. Physics hears something else. It hears a state, a measurable one, a state with the lowest accessible energy compatible with the fields, a state whose fluctuations can influence atoms, a state whose early behavior may have been stretched into galaxies, a state whose energy, in one of the great unresolved tensions in theoretical physics, seems to confront us with a catastrophic mismatch between naive quantum estimates and the tiny observed value associated with cosmic acceleration. That last problem deserves one final glance, even here at the end, because it shows how unfinished the story remains. Quantum field theory, handled in the most straightforward ways, seems to suggest vacuum contributions to energy density that are absurdly larger than what the observed universe appears to permit. Yet the cosmos expands as if there is some small positive vacuum-like energy, often associated with dark energy or the cosmological constant. The mismatch is not subtle. It is one of the worst theoretical predictions in the history of physics, if interpreted naively. That means the vacuum, even after everything we have learned, is still not fully understood, not mastered, not closed. That ignorance matters, because it prevents the ending from becoming smug. The vacuum is not a solved poetic symbol. It is an active frontier, a place where our best descriptions work with terrifying precision in some domains and collide with profound incompleteness in others. We know enough to say that empty space is not empty in the old classical sense. We know enough to measure its effects. We know enough to tie it to the deepest structures of field theory and cosmology. But we do not know enough to pretend the final layer has been reached. The floor is still retreating. Or maybe that is the last emotional truth hidden inside this subject. Not that nothing is secretly everything. That phrase is too easy. The truth is more disciplined. What looked like nothing keeps turning out to be a deeper level of physical reality than our intuition was prepared for. And the deeper we go, the less the universe resembles the categories that made us feel at home inside it. That is not cause for despair. It is a better kind of awe. Not warm awe, not decorative awe, something more restrained. The feeling that comes when the world reveals that it does not need your intuitions in order to be coherent. The feeling of standing before laws that are elegant and real, and, at the same time, not shaped for your comfort. Return to the box one last time, not as an experiment now, but as an image, a sealed volume. The air removed, the dust gone. The ordinary particles absent as far as you can manage. Once, that picture seemed to promise emptiness. Now it promises something harder. A meeting with the lowest state reality will permit there. Not non-being, not philosophical zero, a physical minimum. Quiet, but not mute. Invisible, but not inactive. Seemingly blank, yet capable of leaving bruises in atoms and perhaps scars across the sky. And in that sense, the deepest mistake was never believing that nothing exists. It was believing we would recognize it if it did.